some answers may have been lost long before the questions were ever asked. Throughout ancient history, archaeologists have uncovered cities, monuments, and artifacts that reveal civilizations capable of remarkable precision, planning, and coordination. These structures stand as evidence of knowledge that once existed, but is no longer fully understood. Massive constructions appear in environments that required careful adaptation, while similar design choices emerge across regions with no clear connection. Researchers can document the results, analyze the materials, and estimate timelines, yet the deeper reasoning often remains unclear. As more discoveries come to light, these ancient mysteries suggest that early human civilization may have developed in ways that are far more complex than the explanations we have today. There is a place in Egypt where the sky does not move, where constellations never shift, planets never wander, and time itself seems to have been captured, compressed into a single, silent circle of stone. It does not lie in the open desert, but within the shadowed chambers of the Temple of Hathor, where one of the most controversial artifacts in ancient history continues to defy complete explanation, the Dendera Zodiac. At first glance, it appears to be an ornate ceiling, a symbolic reflection of Egypt's mythological worldview. But the longer you observe it, the more that interpretation begins to collapse. Because this is not simply a depiction of the heavens, it behaves like a system that encodes something precise, something measurable, and something disturbingly accurate. The modern story of the Dendera Zodiac begins in 1798, during Napoleon's expedition into Egypt. Among the engineers, artists, and scholars documenting ancient ruins, one detail immediately stood out: a perfectly circular carving unlike anything ever recorded in Egyptian temple art. It did not follow the familiar linear format of astronomical ceilings found in tombs. It did not tell a story. It organized information. It reduced the sky into structure. By the early 19th century, the artifact had become so controversial that it was removed from Egypt and transported to France, where it remains today in the Louvre Museum. From that moment on, the Dendera Zodiac was no longer just an archaeological discovery. It became a problem, one that could not be easily resolved within the boundaries of known history. At the center of the relief lies a circular arrangement of the 12 zodiac constellations, Aries, Taurus, Gemini, and the rest, rendered with a clarity that suggests more than artistic inspiration. Surrounding them are figures representing planets, celestial forces, and divine beings, each placed with a precision that feels intentional rather than decorative. Their positions are not random. Their relationships are not arbitrary. They form a structure, one that appears to follow rules. For decades, the dominant explanation was that this was a product of cultural exchange during the Ptolemaic period, a blending of Egyptian religious imagery with Greek astronomical knowledge. But that explanation began to weaken as scientific tools advanced, because when researchers started testing the layout against real astronomical data, the results were not vague. They were specific, uncomfortably specific. Using advanced sky reconstruction software, researchers analyzed the relative placement of planetary symbols carved into the zodiac. They compared these positions against known celestial configurations calculated backward through time, and what they found was extraordinary. Multiple independent studies converged on a narrow window, roughly between 60 and 30 BCE. This was not based on artistic style, it was based on alignment. Around 51 BCE, for example, Jupiter would have been positioned in Cancer, while Saturn occupied Capricorn. These positions align closely with the symbolic figures carved into those exact regions of the relief. Mars, Mercury, and Venus also fall into positions that correspond with their real orbital placements during that same period. This is not a loose resemblance. This is a multi-body alignment. The probability of 5 visible planets appearing in correct relative positions within a symbolic system purely by chance is extremely low. In modern statistical modelling, such a coincidence would be considered highly improbable without underlying structure, which leads to a difficult conclusion. Whoever created this relief may have been mapping the sky with intent, and then there are the eclipses. Among the most debated features of the zodiac are circular symbols intersected by serpentine forms, imagery traditionally associated with cosmic disruption in Egyptian belief. Some researchers interpret these as representations of solar and lunar eclipses. When these interpretations are tested against astronomical records, one configuration aligns closely with a solar eclipse dated to March 7, 51 BCE, followed by a lunar eclipse within the same cycle. This is not a simple observation. Predicting eclipses requires understanding long-term periodicity, most notably the Saros cycle, which spans approximately 18 years and 11 days. Ancient Babylonian astronomers achieved this through centuries of recorded data, meticulously preserved across generations. But at Dendera, there is nothing. No written calculations, no observational records, no intermediate steps, only the result, encoded into stone. Archaeological excavations at Dendera throughout the 19th and 20th centuries have only deepened the mystery. Led by figures such as Auguste Mariette, these expeditions uncovered additional astronomical ceilings, inscriptions referencing lunar cycles and systems of decans, star groups used by ancient Egyptians to measure time during the night. These findings confirm that Egyptian priests possessed structured astronomical knowledge. They observed the sky consistently, they tracked cycles, they understood rhythm and repetition in celestial movement. But there is a gap between observation and precision modelling. Tracking stars is one level of knowledge. Mapping planetary motion with multivariable alignment is another entirely. Even more intriguing, the architecture of the temple itself appears aligned with celestial phenomena. Certain corridors and chambers are oriented toward the rising of specific stars at precise times of the year. This suggests that the temple may have functioned not only as a place of worship, but as an observational instrument, a structure designed to interact with the sky. And yet, despite decades of excavation, no physical tools have been discovered that could explain the level of precision seen in the zodiac. No telescopes, no advanced angular measurement devices, no detailed star catalogues, nothing that bridges the gap between what we know and what we see. So how was it created? One possibility is that the Dendera Zodiac is not a snapshot of a single moment, but a composite, a compressed system encoding multiple celestial events into a unified diagram. If this is true, then the creators were not merely observing the sky, they were modelling it, identifying patterns across time, translating those patterns into spatial relationships, encoding complexity into form. In modern terms, this resembles data visualization, an advanced method of compressing multi-layered information into a single structure. If that interpretation holds, then the Dendera Zodiac is not just a map. It is a model of the sky itself. Comparisons with other ancient civilizations only intensify the mystery. Babylonian astronomers relied on numerical tables to predict planetary motion. Greek scientists, including Hipparchus, developed geometric models and even identified the slow shift of the stars known as precession. These systems were analytical, step-by-step, and thoroughly documented. They revealed their process. The Dendera Zodiac does not. No equations, no calculations, no method. It presents only the outcome, a complete multivariable configuration of the sky, without explanation. Some interpretations suggest that the zodiac may even encode awareness of long-term astronomical cycles, possibly including gradual shifts in stellar positions over centuries. Others propose that the knowledge embedded within it was inherited from an earlier civilization, or transmitted through channels that have not survived in the archaeological record. These ideas remain speculative, but they persist for a reason. Because conventional explanations leave critical gaps, especially when confronted with the level of precision that modern science can partially verify, but not fully account for. So what do you think? Is the Dendera Zodiac evidence of advanced ancient astronomy, or a trace of knowledge we were never meant to lose? Share your thoughts in the comments below. It did not begin as a weapon. It began as a phenomenon no one could explain. Witnesses didn't describe ordinary flames. They described something that moved with intent, clung like a living substance, and refused to die. Fire that spread across water. Fire that grew stronger when attacked. Fire that turned the sea itself into a battlefield. This was Greek fire, the most feared weapon of the Byzantine Empire, and more than 1,000 years later, it remains one of the greatest unsolved mysteries in the history of technology. The story unfolds in Constantinople, a city positioned at the intersection of continents, trade routes, and empires. Protected by massive walls and surrounded by water, it was both fortress and target. By the late 7th century, the empire faced one of the greatest threats in its history from the rapidly expanding Umayyad Caliphate. Their fleets were larger, faster, and strategically dominant. Historical estimates suggest that during the First Arab Siege, the attacking forces deployed hundreds of ships, overwhelming Byzantine defences by sheer numbers. By every conventional measure, naval strength, manpower, and positioning, Constantinople should have fallen, but it didn't. Something changed the equation. According to Byzantine chronicles, that turning point came with the arrival of Callinicus of Heliopolis around the year 673. Within a short time, a new weapon appeared, one that could be projected from ships through bronze siphons, reaching distances estimated between 15 and 30 meters. This was not thrown fire. It was directed, controlled, and deployed with precision. During the siege between 674 and 678, entire enemy vessels were reportedly engulfed within seconds. Attempts to extinguish the flames using seawater not only failed, but in some accounts appeared to make the fire spread even more violently. Later records from the siege of 717 to 718 reinforced these claims. Chroniclers describe entire squadrons destroyed in a matter of hours, with flames continuing to burn on the surface of the sea. While medieval accounts often exaggerate, archaeological evidence adds weight to these descriptions. Excavations in the Bosphorus Strait and the Golden Horn have uncovered layers of charred ship remains, burned structural wood, and thick resin-like residues. Radiocarbon dating places these findings between the late 7th and early 8th centuries, exactly when Greek fire was known to be used. The burn pattern suggests temperatures significantly higher than typical wood fires, indicating the presence of an intensified or chemically enhanced combustion process. And yet, despite these traces, no physical sample of Greek fire has ever been identified. No container, no preserved formula, no definitive residue, only descriptions, and those descriptions do not match anything we fully understand. At the core of the Greek fire mystery lies its most elusive and controversial element, its chemistry. For centuries, scientists and historians have attempted to reconstruct its formula using substances known to the Byzantine world. The most widely accepted theory suggests a mixture centered around petroleum derivatives such as naphtha, combined with sulfur, pine resin, and quicklime. Each ingredient appears logical. Naphtha provides a volatile fuel base. Resin increases thickness, allowing the substance to adhere to surfaces. Sulfur enhances ignition and burn intensity. Quicklime reacts with water, producing heat through an exothermic reaction. On paper, this formula seems convincing. In reality, it fails. Modern experimental archaeology has repeatedly attempted to recreate Greek fire using these exact components. The results are consistent and disappointing. The mixtures burn, sometimes intensely, but they do not replicate the key properties described in historical records. They cannot sustain stable combustion on open water. They do not maintain adhesion at the same level. And most critically, they do not exhibit the defining paradox resistance or apparent amplification when exposed to water. This contradiction is not minor. It directly challenges the fundamental principles of combustion. Water absorbs heat and reduces fire intensity by limiting oxygen access. For Greek fire to behave differently, it would require a system capable of generating continuous heat while maintaining structural cohesion in a highly unstable environment. The quicklime reaction, often cited as the explanation, produces heat, but calculations show that it is insufficient to sustain large-scale flames, especially in open sea conditions where dilution rapidly weakens chemical reactions. This suggests one unavoidable conclusion: something is missing. Some researchers propose that Greek fire may have been an early form of chemical emulsion, a stable mixture combining hydrophobic hydrocarbons with reactive compounds in a way that prevented separation and maintained combustion. Others suggest the use of unknown organic thickeners or mineral catalysts, substances that either degraded over time or were never documented. There are even theories that Byzantine engineers possessed a method of refining crude oil far more advanced than previously believed, allowing them to produce a more controlled and potent fuel. When compared to modern incendiary weapons, the mystery deepens further. Napalm, developed in the 20th century, shares some similarities, particularly its adhesive, gel-like nature and ability to burn across surfaces. However, napalm depends on refined petroleum and synthetic stabilizers, products of industrial chemistry that did not exist in the 7th century. White phosphorus offers another comparison, as it can ignite spontaneously and burn at extremely high temperatures, sometimes even underwater. Yet it is unstable, dangerous to handle, and there is no evidence linking it to Byzantine use. In controlled laboratory experiments, no pre-modern mixture has successfully reproduced all three defining characteristics of Greek fire: sustained combustion on water, strong adhesion, and resistance to extinguishing. Each attempt solves part of the puzzle, but never the entire system. It is not just that the formula is lost. It is that the formula, as described, should not exist. Greek fire was not simply a substance, it was a system. Byzantine warships were equipped with bronze siphons capable of projecting streams of burning liquid toward enemy vessels. This required precise control of pressure, flow, and ignition timing. The mixture had to remain stable within its container, fluid enough to be pumped, and volatile enough to ignite upon release without causing catastrophic failure inside the device. Archaeological discoveries support the existence of such systems. Fragments of metal, tubing, valves, and pressure-related components have been found in Byzantine naval contexts. While incomplete, these remains suggest a level of mechanical sophistication that challenges conventional assumptions about early medieval engineering. The integration of chemistry, metallurgy, seats, and fluid dynamics into a single weapon system indicates a coordinated knowledge base that appears far more advanced than expected. Perhaps the most disturbing aspect of Greek fire is not how it worked, but how it disappeared. Unlike other revolutionary technologies such as gunpowder, which spread rapidly across cultures, Greek fire remained tightly controlled within the Byzantine state. Its production was likely restricted to Forged in an age we often dismiss as technologically primitive, The name Ulfberht swords appears carved into steel with a precision that feels almost defiant, as if it were never meant to belong to the 9th century at all, and yet more than 1,000 years later, these blades continue to challenge everything we think we know about the evolution of technology, because they are not simply weapons but anomalies, objects that seem to have arrived too early, carrying with them a level of metallurgical sophistication that should not exist within the known capabilities of early medieval Europe. And when modern science finally examined them in detail, what it discovered was not just impressive. It was deeply unsettling, suggesting that the past may have been far more advanced or at least far less understood than we're willing to accept. The story begins across a vast and interconnected landscape stretching from Scandinavia through the Frankish Empire and deep into Central Europe, where rivers such as the Rhine acted as arteries of trade and movement, and it is along these routes that more than 170 Ulfberht swords have been uncovered through archaeological excavations, many of them found in Viking burial sites in Norway and Germany, carefully placed beside individuals of clear status and wealth, indicating that these were not common tools but elite possessions, possibly restricted by access, cost, or both. And this distribution alone already raises questions, because while ordinary Viking swords were produced locally in large numbers using relatively simple bloomery technology, Ulfberht blades appear in patterns that suggest controlled circulation, almost as if they were part of a specialized network, and when compared side by side with typical swords of the same era, the differences become immediately visible, with smoother surfaces, more refined inscriptions, and edges that seem sharper and more consistent, subtle, visual clues that hinted at something unusual long before science confirmed it. That confirmation came centuries later, not in the field but in laboratories, where metallurgists began subjecting these blades to X-ray imaging, chemical analysis, and microscopic examination, and what they found was extraordinary. Carbon levels ranging from approximately 0.8 to over 1%, far exceeding the typical 0.1 to 0.3% found in standard European iron of the time, along with an almost complete absence of slag inclusions. Those microscopic impurities that are unavoidable in bloomery-produced metal and which weaken the structure of conventional swords, creating stress points that can lead to bending or fracture. Yet in Ulfberht, the metal appears clean, uniform, and highly controlled, closer in structure to modern steel than to anything else known from the Viking Age, and this creates an immediate contradiction, because the dominant European technology of the time, the bloomery furnace, simply could not achieve this level of purity or carbon control, as it operated below the melting point of iron, and produced a semi-solid mass that required repeated hammering to remove impurities, a process that inherently limits precision. And when we compare this to the microstructure observed in Ulfberht blades, the gap becomes impossible to ignore. To bridge that gap, researchers have turned to comparisons beyond Europe, particularly to regions such as Persia and India, where crucible steel production was already known, a process capable of reaching temperatures around 1,500 degrees Celsius and producing high-carbon, low-impurity steel known for its strength and flexibility, and the similarities between this material and the steel found in Ulfberht swords are striking enough to suggest a connection, leading to the theory that Viking trade networks may have imported raw steel or even semi-finished blades from the east, transporting them along routes that link the Baltic to the Byzantine and Islamic worlds. And yet even this explanation, while plausible, does not fully resolve the mystery, because possessing high-quality material is only the beginning. And what truly defines Ulfberht is not just the steel itself, but what was done to it afterward. This is where the story becomes far more complex, because transforming high-carbon steel into a functional sword requires an extraordinary level of skill in forging and heat treatment, processes that are difficult even with modern tools and almost impossibly delicate without them, because steel at around 1% carbon behaves unpredictably under heat, becoming brittle if overheated, cracking if cooled too quickly, and losing hardness if cooled too slowly. And modern metallurgy explains these behaviors through phase transformations, changes in the internal structure of the metal, where austenite forms at high temperatures and transforms into martensite or pearlite depending on the rate of cooling. Processes that must be controlled within extremely narrow margins, often measured in seconds, yet the blacksmiths of the Viking Age had no thermometers, no controlled furnaces, no theoretical understanding of these transformations, relying instead on experience, intuition, and sensory cues such as colour, sound, and resistance. Methods that, while effective to a degree, are not typically associated with the level of precision required to consistently produce high-performance steel, and yet the evidence suggests that they did exactly that, because surviving Ulfberht blades display a remarkable balance between hardness and flexibility, confirmed through hardness testing that places their edges at approximately 55 on the Rockwell scale, a level comparable to high-quality medieval swords produced centuries later, while their cores remain resilient enough to absorb impact without breaking, indicating the use of differential heat treatment, a technique in which different parts of the blade are cooled at different rates to create a hardened edge and a softer spine, a method that requires careful timing, precise temperature control, and an understanding, whether conscious or intuitive, of how heat moves through metal. And this is where modern attempts to replicate Ulfberht have consistently encountered problems, because even with advanced knowledge and equipment, experimental archaeologists and skilled blacksmiths often fail to reproduce the same microstructural consistency, with blades either becoming too brittle due to excessive martensite formation or too soft due to insufficient carbon retention, and demonstrating just how narrow the margin for success truly is, and highlighting a gap between what we can measure and what we can actually recreate. This gap becomes even more intriguing when we consider that not all Ulfberht swords are equal, because among the 170 known examples, there is a clear division between high-quality blades and lower-quality imitations, with some containing the same high-carbon, low-impurity steel described earlier, while others are made from standard bloomery iron with visible slag inclusions, and even the inscriptions themselves vary, with some precisely formed as plus Ulfberht plus, and others showing irregular spacing or misspellings, suggesting that the name itself may have functioned as an early form of branding, a mark associated with superior quality that was widely copied, was much like modern counterfeit goods, and this introduces a fascinating social dimension to the mystery, implying that people of the time were aware of the difference, that they recognized certain blades as exceptional, and that demand for such weapons was strong enough to inspire imitation, and then, just as abruptly as they appear in the archaeological record, they begin to disappear, because after the early 11th century, high-quality Ulfberht swords become increasingly rare, and the level of metallurgical sophistication they represent does not continue in a clear line of development, but instead seems to vanish, replaced by more conventional techniques before eventually re-emerging in different forms centuries later. And this raises one of the most difficult questions of all. Why would such an advanced and effective technology be lost, rather than refined and expanded, especially in a context where superior weapons would have provided significant advantages, and several explanations have been proposed, including the disruption of long-distance trade routes that may have supplied high-quality steel, particularly as connections with the Islamic world weakened, as well as the possibility that the knowledge required to forge and treat this material was limited to a small group of specialists, perhaps even a single lineage of craftsmen whose methods were never written down and were lost over time. What do you think truly created the Ulfberht swords? A lost technology, or a secret we still don't fully understand? Share your thoughts in the comments below. Time, in the ancient world, was never supposed to look like this, not carved into stone with numbers that stretch millions, perhaps billions, of years into the future, not measured with a precision that rivals early modern science, and certainly not encoded by a civilization without telescopes, metal instruments, or any known form of advanced optics. Yet across the dense jungles of Mesoamerica, among the ruins of cities like Tikal, Palenque, and Coba, archaeologists uncovered something that does not behave like a primitive calendar at all. It behaves like a system, structured, calibrated, and astonishingly precise. This is the Maya long count calendar, a timeline that does not repeat, but extends forward and backward through time, assigning each day a fixed position in an almost infinite sequence. The story of its discovery was not a single breakthrough, but a slow unraveling of meaning hidden in stone. 19th century explorers first documented towering stelae covered in intricate glyphs, assuming them to be symbolic or ceremonial. But as epigraphers and archaeologists pushed deeper into the 20th century, patterns began to emerge, repeating numerical structures embedded within the inscriptions. These were not decorative markings, they were dates, exact, calculated, repeatable dates. Excavations carried out under institutions such as the Carnegie Institution revealed that these numerical systems were consistent across vast regions, from the lowland jungles of Guatemala to the Yucatan Peninsula. What initially appeared as isolated artistic traditions gradually revealed itself as a unified, highly organized method of recording time, one that demanded mathematical consistency and long-term observational accuracy. At its core, the long count operates on a base 20 system, yet with a deliberate and highly unusual modification. Instead of following a pure vigesimal progression, the Maya defined one crucial unit, the ton, as 18 times 20 days, or 360 days. This is not mathematically natural, it is astronomically intentional. It aligns almost perfectly with the solar year, revealing that the system was not merely invented but engineered. The Maya were not just counting, they were calibrating. They were bending numerical structure itself to mirror the rhythms of the cosmos. And this is where the mystery deepens, because such calibration requires not only observation, but consistency. Data collected, compared, and refined over generations. Nowhere is this more evident than in their tracking of the planet Venus. To the Maya, Venus was far more than a celestial object. It was a temporal anchor, a predictive force, and possibly even a symbol of power tied to ritual cycles. Within the surviving pages of the Dresden Codex, one of the most important pre-Columbian texts ever discovered, lies a detailed set of tables dedicated entirely to Venus. These tables record its synodic cycle, the time it takes to return to the same position in the sky relative to Earth. Modern astronomy places this cycle at approximately 583.92 days. The Maya recorded it as 584 days. The difference, less than 1/10 of a day, is so small that it results in a deviation of only 1 day after more than 12 years of continuous tracking. Even more astonishing, the Dresden Codex does not simply record this cycle, it corrects it. The tables include built-in adjustment intervals indicating that the Maya were aware of cumulative error and had developed a method to compensate for it. This is not passive observation, this is active correction, an early form of scientific methodology. Over 5 Venus cycles, nearly 8 years, their system maintains an error margin of less than half a day. Over decades, it remains functionally precise. Such accuracy, achieved without telescopes, without optical lenses and without mechanical instruments, stands in stark contrast to the capabilities of other civilizations at the time, and to understand the magnitude of this achievement, comparison becomes unavoidable. European astronomers during the medieval period, working more than a millennium later and with access to more advanced mathematical frameworks, often struggled to reach similar levels of precision. It was not until the 17th century, with figures such as Johannes Kepler, that planetary motion began to be described with comparable accuracy using elliptical orbits. And yet the Maya, relying solely on naked eye observation, achieved results that approach these later scientific breakthroughs. This raises a fundamental question. How does a civilization without modern tools reach such a level of observational consistency? Archaeology provides part of the answer, etched not in theory, but in architecture. At Chichen Itza, the structure known as El Caracol stands apart from other buildings in both form and function. Circular in design and punctuated by narrow windows, it appears almost purpose-built for observation. Detailed studies have shown that these openings align with the extreme rising and setting points of Venus on the horizon. These are not rough estimates, they are precise sightlines, embedded into stone. The building itself functions as an instrument, fixed, stable, and aligned with celestial motion. Similar alignments have been documented across the Maya world: pyramids oriented towards solstices, staircases designed to cast shadow serpents during equinoxes, and stelae placed in positions that correspond to astronomical events. Excavations at Tikal have revealed inscriptions bearing long count dates that align with known celestial occurrences, and are reinforcing the idea that these were not symbolic or mythological references, but records of real, observed phenomena. Over the course of the 20th and 21st centuries, continued archaeological work has strengthened this pattern. The Maya were not merely constructing cities. They were constructing observational systems, embedding astronomical knowledge into the very fabric of their environment. Their understanding extended beyond Venus. The Dresden Codex also contains eclipse tables, records that identify periods during which solar and lunar eclipses were likely to occur. While these tables do not specify exact geographic visibility, they define time windows with remarkable accuracy, based on repeating cycles that closely match modern astronomical models of eclipse seasons. This implies a deep understanding of periodicity, and as well as the ability to recognize patterns across long spans of time. It suggests a civilization capable of collecting and preserving astronomical data across generations, refining it into predictive systems that functioned reliably over decades. And yet, perhaps the most unsettling aspect of the long count is not its precision, but its scale. The widely known cycle of 13 Baktuns, equivalent to approximately 394 years, represents only a fraction of the system's full range. Higher-order units allow for the representation of dates millions, even billions of years into the past or future. At Koba, inscriptions reference time spans so vast that they exceed the entirety of recorded human history. This is not practical timekeeping. It is conceptual time, time treated as an infinite continuum. And why would a civilization need such a system? What purpose does it serve to track moments that lie far beyond any conceivable human experience? Layered onto this is the integration of multiple calendars operating simultaneously. Something doesn't add up, and it begins with a material that by every known standard of ancient technology simply should not be there. High in the desolate, wind-scoured ridges of the Bayan Kara-Ula Mountains, where altitude strips the air thin and the landscape erases almost every trace of human continuity, a story emerged that refuses to settle comfortably within the boundaries of conventional archaeology. It centers on the enigmatic Dropa stones, a series of stone discs whose alleged characteristics if even partially accurate, challenge not only our understanding of ancient craftsmanship, but the entire framework through which we interpret technological evolution in prehistory. The narrative traces back to the early 20th century, when reports surfaced of expeditions venturing into isolated cave systems embedded within these mountains. According to descriptions that would later circulate in fragmented publications, these caves were not entirely natural. Their interiors appeared smoothed, almost engineered, as if shaped with intent rather than carved solely by geological processes. Within these chambers, explorers allegedly encountered rows of skeletal remains, small in stature, fragile in structure, and described as possessing proportions that did not align neatly with known human populations of the region. Alongside them lay hundreds of circular stone discs, each measuring approximately 30 centimeters in diameter, each featuring a precisely drilled central hole, and each marked by a continuous spiral groove extending from the center to the outer edge. At a superficial level, such objects might be interpreted as ritual artifacts or symbolic carvings, not uncommon in ancient contexts. However, the reported precision of these grooves introduces a complication. Experimental archaeology provides a useful benchmark here. When modern researchers attempt to replicate continuous spiral engravings on hard stone using tools consistent with Neolithic or early Bronze Age technology, the results invariably show irregularities, variations in depth, inconsistencies in spacing, and interruptions caused by tool wear or manual fatigue. Yet descriptions of the Dropa discs repeatedly emphasize uniformity, a continuous, evenly spaced spiral, as if produced by a controlled rotational mechanism rather than by hand. This alone raises questions about technique, but it is not the geometry that defines the deepest anomaly, it is the material itself. In the 1960s, a series of reports, often cited, rarely verified, claim that fragments of these discs underwent laboratory analysis. The conclusions, if accurate, would be profoundly disruptive. The stone was said to contain an unusually high concentration of cobalt, not incidental traces that might be attributed to natural mineral inclusion, but a measurable and consistent presence embedded within the material. In modern science, cobalt is not a trivial element. It is associated with high-temperature alloys, magnetic systems, and energy storage technologies. Its extraction and refinement require controlled processes and significant heat, conditions that, according to current archaeological evidence, were not achievable in the prehistoric periods to which these discs are often attributed. To understand why this is so significant, it is necessary to examine the broader timeline of material usage in ancient societies. During the Neolithic era, spanning roughly 10,000 to 4,000 years ago, human tool-making was dominated by stone, flint, obsidian, and other silicate materials selected for their predictable fracture patterns. These materials allowed for precise shaping but did not involve chemical transformation. The subsequent Bronze Age marked a major technological shift, introducing metallurgy through the alloying of copper and tin. Even then, the process required controlled furnaces and an understanding of ore behavior that developed gradually over centuries. Iron, which demands even higher smelting temperatures, did not become widespread until approximately 1200 BCE. Cobalt, however, belongs to an entirely different category of complexity. While it does occur naturally in certain ores, isolating it in usable form requires advanced knowledge of separation techniques and sustained high-temperature processing. In known ancient contexts, cobalt appears only in limited and specialized applications, most notably as a pigment in glass and ceramics in regions such as ancient Egypt and Mesopotamia. Even in these cases, its use was controlled, minimal, and clearly tied to decorative or symbolic purposes. There is no verified precedent for cobalt being integrated into structural stone artifacts, and certainly none in remote high-altitude environments lacking evidence of industrial activity. And yet, the claims surrounding the Dropa stones go further still. Some accounts suggest that the discs exhibited weak electrical conductivity. This is where the anomaly transitions from unusual to deeply perplexing. Stone, in its natural state, is typically an electrical insulator. The introduction of metallic elements can alter this property, but only under specific conditions, namely, when conductive materials are distributed in a way that allows electron flow. Such distribution does not occur randomly. It implies either deliberate mixing or a naturally occurring composite structure of remarkable uniformity. In either case, the presence of conductivity in a shaped artifact raises the possibility, however speculative, of intentional design. If one entertains this possibility, even cautiously, it leads to a series of unsettling questions. Why would an ancient society embed conductive material within a precisely carved disc? What function could such an object serve? One hypothesis, frequently proposed but never substantiated, suggests that the spiral grooves themselves may have played a role beyond decoration. In modern technology, spiral grooves are used as a means of encoding information. Vinyl records, for instance, store sound through microscopic variations along a continuous track, which can be read mechanically and converted into audio signals. The structural similarity between such systems and the described form of the Dropa discs is striking, not in proof, but in pattern. Patterns in science demand attention. Further reports describe microscopic markings within the grooves, inscriptions so fine that they allegedly required magnification to observe. These markings were interpreted by some as a form of symbolic language, perhaps even a recorded narrative. One particularly controversial claim suggested that the discs documented the arrival of a non-human group stranded on Earth. This interpretation has been widely dismissed by the scientific community, largely due to the absence of verifiable artifacts and the lack of reproducible analysis. No original discs have been made available for independent study, and no peer-reviewed publications have confirmed these findings. This absence of evidence is the central problem. There are no officially documented excavations, no museum collections displaying authenticated samples, no laboratory data that can be independently verified. The Dropa stones exist primarily in secondary accounts, fragments of reports, translated articles, and repeated retellings that have evolved over time. For many researchers, this is sufficient grounds to reject the entire narrative as a fabrication or a misinterpretation amplified through repetition. And yet, history has shown that anomalies are not always illusions. The Antikythera mechanism was once considered an impossibility, an object so mechanically advanced that it appeared centuries ahead of its time. Only through a technology capable of surviving extreme heat, preserving fragile structure, and defying modern replication exists, yet it comes not from a modern laboratory, but from an ancient civilization long lost to history. Across the iron-rich soils of the Jos Plateau in Nigeria, archaeologists have uncovered fragments of a system that should not exist in the form we find it today: the terracotta sculptures of the Nok culture. At first glance, they appear as powerful artistic expressions, elongated human faces, geometrically pierced eyes, and elaborate hairstyles rendered with confidence and abstraction. But behind their striking appearance lies something far more complex. These objects were not merely crafted. They were engineered through a process that required control over heat, material, and structure at a level that should not have been possible for a society without written knowledge or visible industrial infrastructure. The discovery of this culture was accidental. In the 1940s, tin miners working across central Nigeria began uncovering unusual terracotta fragments buried in the soil. These pieces eventually reached British archaeologist Bernard Fagg, who recognised their significance and identified them as part of an unknown ancient civilization. Over the following decades, archaeological investigations expanded the known extent of knock sites across hundreds of square kilometres. By the early 2000s, systematic excavations led by researchers such as Peter Brunigs and Nicole Rupp introduced modern scientific methods into the study of knock artifacts. Thermoluminescence dating confirmed that these sculptures were created between approximately 1000 BCE and 300 CE. Yet the true shock was not their age, it was their technical sophistication. Laboratory analysis revealed that many knock terracotta sculptures have been fired at temperatures ranging from 900 to over 1100 degrees Celsius. To understand why this matters, comparison is essential. In most prehistoric contexts, open firing methods typically reach only 600 to 800 degrees Celsius. Even in established Neolithic ceramic traditions in Europe, objects fired above 800 degrees often display structural defects, cracking, warping, or weakness. Yet the knock sculptures, despite being hollow, thin-walled, and geometrically complex, survive temperatures far beyond this range. This implies not just high heat, but controlled heat. And yet, unlike later civilizations, no permanent kilns, no ventilation systems, and no enclosed firing chambers have been found. But the temperature is only part of the story. The true mystery lies in something far more difficult to achieve: the ability to prevent cracks and deformation under extreme thermal stress. Many knock figures are hollow, with walls sometimes less than 1 centimetre thick. Their forms are asymmetrical and intricate, with perforations, extended features, and delicate structures that would normally fail during firing. In modern ceramic engineering, these characteristics represent a critical challenge. Uneven thickness leads to uneven heat distribution. Uneven heat produces internal stress gradients, and these stresses often exceed the material's strength, resulting in thermal shock, cracks, warping, or complete collapse. Even today, producing large hollow ceramic forms with thin walls requires carefully programmed kilns and controlled heating and cooling cycles. And yet, the knock achieved this consistently. Experimental archaeology offers a crucial comparison. In attempts to recreate knock-style sculptures using historically plausible techniques, researchers in the early 21st century encountered high failure rates. When producing hollow figures with thin walls and complex shapes, between 40 and 60% of pieces failed during firing. Cracks appeared along stress lines. Structures warped as clay softened under heat. Some forms collapsed entirely before reaching peak temperature. And even with modern knowledge of material science, consistent success remained elusive. The knock, however, appear to have mastered a repeatable process. This leads directly to the most critical and unresolved mystery: their method of preventing cracks and deformation, a technique that has not yet been fully reconstructed. In ceramic science, avoiding structural failure requires balancing multiple variables at once: material composition, heat distribution, airflow, structural support, and cooling rate. Modern kilns achieve this through insulation and precise control systems. The knock left behind none of these. No permanent kilns, no flues, no chambers, only the finished results. Several theories attempt to explain this. One suggests that knock artisans used a multi-stage firing process, a slowly increasing temperature to allow moisture to escape evenly, reducing internal stress. Another points to the use of tempering materials, fine inclusions such as crushed pottery, quartz, or organic fibers mixed into the clay. Microscopic analysis confirms that Nok terracotta contains a consistent distribution of these materials, suggesting a controlled and standardized preparation process. These inclusions help absorb stress and prevent cracks from spreading. But even this does not fully explain the near absence of deformation, because deformation is not simply about cracks, it is about maintaining shape under heat. As clay reaches high temperatures, it softens. In hollow forms, gravity becomes a threat. Without support, structures sag, edges distort, and symmetry is lost. Preventing this requires either internal reinforcement or external stabilization. Some researchers propose that Nok artisans use temporary internal supports made from organic materials that burned away during firing. Others suggest that sculptures were partially buried in ash or surrounded by insulating material to stabilize both temperature and structure. These ideas are plausible, but they remain unproven. More importantly, modern experiments using similar techniques have not achieved the same level of consistency. What makes this mystery even more compelling is its scale and consistency. Nok terracotta fragments found across multiple sites, sometimes separated by vast distances, share similar material composition, firing characteristics, and structural resilience. This was not accidental success, it was a system. A repeatable process maintained across generations without written documentation. A form of knowledge embedded entirely in practice. When compared globally, the anomaly becomes even clearer. In ancient Egypt, ceramic production was widespread, yet rarely combined high firing temperatures with thin-walled, complex hollow structures without visible deformation. In early Chinese ceramic traditions, advanced kiln designs, such as dragon kilns, were required to achieve similar control, and these structures left clear archaeological traces. The Nok achieved comparable results, without leaving behind the tools we would expect. This raises a deeper question. Was Nok technology the result of centuries of experimentation, or a level of understanding modern science has yet to fully grasp? Their artisans may have mastered fire and material through intuition, reading flame, sound, and subtle changes in clay in ways that cannot be easily recorded or replicated. Today, their kilns remain invisible. No structures, no blueprints, only results that defy expectation. Each fragment is not just an artifact, but evidence of a system we still cannot reproduce. And the question remains, what did they know that we have forgotten? Share your thoughts in the comments below. Hidden beneath the sands of Saqqara for more than 5 millennia, the mysterious Sabu disk came to light in 1936 during excavations led by Walter Bryan Emery inside Mastaba S3111, a First Dynasty tomb belonging to an official named Sabu, dated to approximately 3000 BCE. At first glance, the object appears almost modest, a circular stone disc roughly 61 centimeters in diameter. But this initial impression quickly gives way to a far more unsettling realization. The disc is unlike any other artifact from its time. It consists of a central cylindrical hub connected to 3 thin, symmetrically curved lobes that extend outward in a design strikingly reminiscent of modern mechanical components such as impellers or rotary blades. This resemblance is not merely aesthetic, but it introduces a profound contradiction when placed within the technological context of early ancient Egypt, a period traditionally understood to rely on relatively simple tools and manual craftsmanship. The core of the mystery lies in the material and the extraordinary technical demands required to shape it. The Sabu disk is carved from schist, a metamorphic rock known for its foliated, layered structure. In geological terms, schist is inherently brittle and prone to splitting along its natural planes when subjected to stress, especially torsional forces or uneven pressure. Unlike granite or basalt, materials commonly used in ancient Egyptian construction and sculpture due to their durability, schist is notoriously difficult to work when thin precision is required, yet the Sabu disk defies these limitations in a way that continues to puzzle modern researchers. Each of its 3 lobes is remarkably thin, in some areas only a few millimeters thick, and exhibits a consistent curvature that suggests a high degree of control during the carving process. The transitions between the central hub and the outer extensions are smooth and continuous, with no visible signs of cracking, delamination, or structural failure. For a material that should theoretically fracture under such conditions, this level of integrity raises immediate and unresolved questions. To appreciate the anomaly, it is essential to compare the Sabu disk with other artifacts from the same era. Excavations across Saqqara, Abydos, and other early dynastic sites have revealed a wide range of stone vessels, tools, and ceremonial objects, many of which demonstrate impressive craftsmanship. However, these objects typically adhere to relatively simple geometries: cylindrical bowls, conical jars, and symmetrical containers shaped through grinding and abrasion using stone tools and sand. Even the finest thin-walled vessels discovered at Abydos, often cited as examples of advanced early stonework, lack the complex multi-directional curvature and structural delicacy seen in the Sabu disk. Moreover, those vessels are usually made from more stable materials such as alabaster or diorite, which can withstand the stresses of shaping far better than schist. The leap from these conventional forms to the intricate blade-like geometry of the Sabu disk is not gradual, it is abrupt and unexplained. Experimental archaeology has attempted to bridge this gap, but with limited success. Modern artisans and engineers have tried to replicate the disk using tools believed to have been available around 3000 BCE, including copper chisels, flint implements, and abrasive sands. In controlled experiments, attempts to carve similar thin, curved structures from schist often result in immediate fracture, particularly when the material is subjected to lateral pressure or vibration. Even when modern craftsmen, equipped with a detailed understanding of material properties, attempt the process, achieving the same level of symmetry and thinness without breakage proves extraordinarily difficult. Some reconstructions suggest that producing such a form would require not only exceptional skill, but also a method of stabilizing the material during carving, potentially involving rotational movement or controlled support mechanisms. This has led to speculation about the use of primitive lathe-like devices, yet no archaeological evidence supports the existence of such technology in early dynastic Egypt. Adding further complexity are modern engineering analyses and digital simulations of the disk's geometry. When modelled using contemporary software, the distribution of mass and curvature appears optimized in a way that reduces stress concentration, a principle central to modern mechanical design. The 3 lobes are not randomly shaped. Their spacing and curvature suggest a balanced configuration that could, in theory, support stable rotation. In some studies, 3D printed replicas of the Sabu disk have been tested in fluid dynamics experiments, demonstrating the ability to generate vortex-like flow patterns and directional movement in both air and liquid environments. While these findings do not confirm a mechanical function, they strongly indicate that the object's shape follows underlying physical principles rather than purely decorative intent. This raises a critical question. Was this level of geometric sophistication the result of intuitive craftsmanship? Or does it point to a deeper, now lost understanding of engineering concepts? The archaeological context in which the disk was found offers few answers. Mastaba S3111 contained a typical assemblage of early dynastic grave goods, stone vessels, tools, and personal ornaments, none of which share the disk's unusual morphology. Subsequent excavations at Saqqara and other First Dynasty sites have failed to uncover additional examples of similar design, reinforcing the idea that the Sabu disc is either a unique artifact or part of a highly limited tradition that has left little trace. This absence of parallels complicates interpretation, as archaeology relies heavily on patterns and repetition to establish function and meaning. Without comparable objects, the disc remains isolated, resisting easy classification. Mainstream Egyptology tends to interpret the Sabu disc as a ceremonial or symbolic object, possibly a type of offering tray or ritual vessel. However, this explanation is not without its shortcomings. The open lobe structure is impractical for containing liquids, and there is no evidence of residue or wear that would suggest repeated use in a ritual context. Furthermore, the complexity of its design seems disproportionate to a purely symbolic function, especially when simpler and more robust alternatives were readily available to ancient artisans. As a result, some researchers argue that the ritual object label may function more as a placeholder than a definitive explanation, reflecting the limits of current understanding rather than a resolved interpretation. In the broader framework of ancient technological development, the Sabu disc presents a significant anomaly. It does not fit within the expected progression from simple to complex forms, nor does it have clear antecedents or successors. Instead, it appears as a sudden and isolated expression of advanced design, embodying principles of symmetry, balance, and material efficiency that are more commonly associated with much later periods. Whether this represents an isolated experiment by an exceptionally skilled artisan, a lost lineage of craftsmanship, or evidence of techniques that have yet to be identified remains an open question. If the Sabu disc was truly created over 5,000 years ago using such a fragile material like schist, do you think it's just a ceremonial object, or evidence of a technology we still don't fully understand? Share your thoughts in the comments below. Some objects do not simply belong to the past, they seem to challenge it. The Klerksdorp spheres, discovered in the mining regions near Ottosdal, South Africa, are among the most unsettling examples. At first glance, they resemble precision-crafted artifacts rather than geological formations. Small metallic-looking spheres marked by straight, parallel grooves that appear almost engineered. Yet these objects were not found in any archaeological layer associated with human civilization. Instead, they were embedded deep within deposits of pyrophilite rock dated to approximately 3 billion years old, a time when Earth itself was still dominated by primitive microbial life, long before the emergence of complex organisms, let alone intelligent toolmakers. This alone transforms the spheres from a geological curiosity into a conceptual anomaly, enforcing a confrontation between what is observed and what is considered possible. The spheres themselves vary in size, typically ranging from 2 to 10 centimeters in diameter. While some are nearly perfect spheres, others take on slightly flattened or disc-like forms, yet still maintain a remarkable degree of symmetry. Their surfaces are often smooth, sometimes metallic in appearance, and in several cases they feature 3 distinct parallel grooves encircling their midsection. These grooves are not random scratches or erosion marks, they are consistent in spacing, depth, and alignment, forming what appears to be a deliberate pattern. This is one of the most debated features, as it evokes comparisons to lathe machining or rotational tooling techniques associated with modern industry. Under magnification, the grooves maintain a level of linear precision that seems out of place in naturally formed mineral concretions. From a compositional standpoint, many of the spheres are made primarily of hematite or goethite, iron-rich minerals commonly found in sedimentary environments. Some specimens display a layered internal structure, with concentric shells surrounding a core, suggesting a process of gradual mineral accretion over time. In certain cases, the outer shell is significantly harder than the surrounding rock matrix, an inversion of what might be expected if these were simple concretions formed by precipitation within softer sediment. This contrast has led to further scrutiny, as it implies a selective mineralization process that may not fully align with typical geological models. The host rock, pyrophyllite, is relatively soft, rated around 3 on the Mohs hardness scale, yet some of the spheres exhibit greater resistance to abrasion, raising questions about the conditions under which they formed. Scientifically, the dominant explanation classifies Klerksdorp spheres as a form of natural concretion, similar in principle to the Moai marbles found in the Navajo sandstone of the southwestern United States, or the cannonball concretions of North Dakota. These formations occur when mineral-rich fluids precipitate around a nucleus, gradually building up a spherical mass over long periods. However, when these analogues are examined closely, critical differences emerge. Moai marbles, for example, tend to have irregular surfaces, lack consistent geometric features, and do not display the kind of parallel grooving seen in Klerksdorp specimens. Thus, cannonball concretions, while sometimes large and spherical, similarly lack any form of structured surface patterning. In both cases, the formations are clearly natural, but they do not replicate the specific combination of symmetry and linear detail observed in the South African spheres. The debate intensifies when considering the context of discovery. These spheres have been uncovered primarily through mining operations, rather than formal archaeological excavations, particularly in the 20th century as pyrophyllite deposits were extracted for industrial use. Workers reported encountering the spheres embedded within solid rock, not in loose sediment, indicating that they formed or were placed prior to the lithification of the host material. While there is no evidence of systematic excavation campaigns dedicated exclusively to the spheres, samples have been collected, analysed and displayed in institutions such as the Klerksdorp Museum, where they continue to attract both scientific and public interest. The absence of a controlled archaeological context complicates interpretation, as it limits the ability to reconstruct precise formation conditions or stratigraphic relationships. This brings us to the most critical dimension of the mystery: the tension between scientific interpretation and controversial hypotheses. Within the framework of mainstream geology, the spheres are understood as natural products of sedimentary and metamorphic processes. Variations in pressure, temperature, and chemical composition could theoretically produce unusual shapes, and including banding or layering. The grooves in this view may be the result of differential weathering, where harder and softer mineral layers erode at different rates, leaving behind linear depressions that mimic artificial markings. Additionally, tectonic stress or microfracturing during rock formation could impose directional features that later become visible as grooves. Yet even within this explanation, there are unresolved inconsistencies. Natural banding typically follows internal mineral boundaries, not perfectly aligned external paths that wrap around an object with such uniformity. Moreover, if the grooves were the result of erosion, one would expect variability, irregular depths, discontinuities, or asymmetry, rather than the repeated appearance of evenly spaced parallel lines across multiple specimens. Statistical comparisons are limited due to the relatively small number of well-documented samples, but anecdotal reports suggest that the grooved spheres represent a distinct subset rather than random outliers. This raises the question of whether a single geological mechanism can account for all observed features or whether multiple processes must be invoked. Outside the scientific consensus, alternative interpretations have gained traction, particularly in popular media and fringe research communities. Some propose that the spheres are remnants of an unknown prehistoric technology, artifacts left behind by a civilization that predates known history by billions of years. Others extend this idea further, suggesting extraterrestrial origins or the possibility that the spheres are part of a larger, an undiscovered system of ancient engineering. These hypotheses often point to the apparent precision of the grooves and the improbability of such features arising naturally as evidence of intentional design. However, they face significant challenges. There is no supporting evidence of associated tools, infrastructure, or cultural context, and the extreme age of the surrounding rock makes the existence of advanced life forms at that time highly unlikely based on current biological and fossil records. A more measured perspective acknowledges that while the spheres are almost certainly natural, they may represent a rare or poorly understood geological phenomenon. Earth's history spans billions of years, encompassing environmental conditions that differ dramatically from those observed today. Or it is possible that the processes responsible for the Klerksdorp spheres are either no longer active or occur under such specific conditions that they are rarely replicated. In this sense, the spheres do not necessarily overturn scientific understanding, but instead highlight its limits, pointing to gaps in our knowledge of mineral formation under extreme or ancient conditions. What do you think? Are the perfectly aligned grooves on the Klerksdorp spheres just a random product of nature, or traces of something beyond our current understanding? Leave your thoughts in the comments below. At the edge of the ancient necropolis of Abu Sir, just south of the pyramids of the Giza Plateau, lies one of the most enigmatic architectural platforms ever constructed in the Old Kingdom, the Sun Temple of Nusayr at Abu Gurab Sun Temple. Unlike the monumental pyramids that dominate the skyline of ancient Egypt, this site presents something far more subtle yet deeply perplexing. A vast ceremonial complex centered around a massive, precisely crafted black basalt platform whose purpose, method of construction, and astronomical significance continue to challenge modern understanding. Built around the 25th century BCE, during a period when solar worship reached a peak in Egyptian religious ideology, the temple appears at first glance to be a ritual center dedicated to the sun god Ra. Yet, as excavations and analyses have shown, the design and execution of its core structure suggest a level of intentionality and technical sophistication that extends far beyond simple religious symbolism. The most striking feature of the complex is the central basalt platform, often described as an altar but differing dramatically from conventional ritual installations found elsewhere in ancient Egypt. Measuring several meters across and composed of extremely hard volcanic stone, the platform exhibits a degree of flatness and geometric precision that is difficult to reconcile with the known toolkits of the 5th dynasty. Basalt, with a hardness of approximately 6 on the Mohs scale, would have required either prolonged abrasion using quartz sand or techniques that remain poorly understood. Copper tools, commonly used at the time and with a hardness of roughly 3, are theoretically capable of shaping such stone only through labor-intensive processes involving indirect abrasion. However, the surface finish observed on the Abu Ghurab platform suggests not only functional shaping, but also deliberate polishing, producing a smoothness comparable in some areas to later high-precision stonework, seen in structures like the Great Pyramid of Giza or certain granite elements in the Valley Temple. This raises a persistent question. Were the ancient Egyptians employing methods of stone finishing that have not survived in the archaeological record, or are we underestimating the efficiency of known techniques when applied at scale? Or yet it is not merely the material or craftsmanship that elevates this structure into the realm of enduring mystery. It is its orientation and spatial integration within the broader temple layout that demand closer scrutiny. The entire complex is aligned along a near-perfect east-west axis, a feature that is not uncommon in Egyptian religious architecture, but takes on heightened significance here due to the absence of enclosed chambers or roofed sanctuaries. Instead, The temple is largely open to the sky, with the basalt platform positioned in such a way that it receives direct sunlight during key moments of the solar cycle. Archaeological surveys conducted in the late 19th century by German expeditions, followed by more detailed studies in the 20th century, documented that during sunrise and sunset at specific times of the year, particularly around the equinoxes, the angle of incoming sunlight falls directly across the platform's surface, illuminating it in a manner that appears both intentional and symbolically charged. This phenomenon becomes even more compelling when considered alongside the original presence of a large obelisk, now lost but known through its massive foundation remains. Obelisks in ancient Egypt were often associated with the petrified rays of the sun, serving as monumental markers of solar power. In the case of Abu Ghurab, the obelisk would have stood in alignment with the platform, potentially casting a shadow that moved predictably across the courtyard throughout the day. If reconstructed hypothetically, the geometry suggests that this shadow could have interacted with the basalt surface in a controlled and measurable way, effectively transforming the entire complex into a kind of solar instrument. While not a machine in the modern sense, the temple may have functioned as a calibrated environment for observing the passage of time, tracking seasonal shifts, or marking ritual calendars tied to solar events. Comparisons with other ancient sites reinforce the possibility that such alignments were not accidental. At Stonehenge, for example, the positioning of stones corresponds precisely with the solstitial sunrise and sunset, suggesting a deliberate attempt to encode astronomical knowledge into architecture. Similarly, Isa temples at Karnak and Abu Simbel demonstrate axial alignments that allow sunlight to penetrate inner sanctuaries on specific dates. However, what distinguishes Abu Ghurab is the combination of open-air design, reflective stone surface, and central placement of a geometrically refined platform. Unlike enclosed temples where light is channeled through corridors, here the entire sky becomes part of the architectural system, and the platform acts as a focal plane for solar interaction. Further complicating the picture is the lack of explicit textual evidence describing the function of this arrangement. While inscriptions from the 5th dynasty emphasize the importance of Re and the king's role as his earthly representative, they do not provide technical descriptions of how temples like Abu Ghurab were intended to operate. Excavations led by Ludwig Borchardt and subsequent archaeological teams uncovered relief fragments, offering scenes and structural remains, but no definitive explanation for the platform's purpose. This absence of documentation forces modern researchers to rely heavily on physical analysis, comparative architecture, and experimental archaeology, approaches that, while valuable, leave room for interpretation and debate. From a scientific perspective, one of the most challenging aspects is determining whether the observed alignments could have been achieved using the measurement techniques available at the time. Ancient Egyptian surveyors are known to have used simple but effective tools such as sighting rods, plumb lines, and merkets, astronomical instruments that allowed them to track stars and establish cardinal directions. These methods were sufficient to produce remarkably accurate orientations in many structures, including pyramids whose sides deviate from true north by only a fraction of a degree. However, translating such large-scale directional accuracy into precise, repeatable solar interactions with a flat reflective surface introduces an additional layer of complexity. It implies not only an understanding of solar motion, but also the ability to predict how light would behave across a specific plane at different times of the year. This leads to a broader and more provocative question. To what extent did the builders of Abu Ghurab conceptualize their temple as an interface between architecture and cosmic phenomena? If the platform was intentionally designed to interact with sunlight in measurable ways, and then it represents more than a ritual object, it becomes a medium through which celestial cycles were observed, interpreted, and perhaps even ritualized. In this sense, the temple could be seen as an early form of scientific instrument, embedded within a religious framework that gave meaning to its operation. Such an interpretation does not require invoking lost technologies or anachronistic machinery, but it does demand a reassessment of how advanced and integrated ancient Egyptian knowledge systems may have been. Despite more than a century of study, the Abu Gurab Sun Temple still holds many unanswered mysteries. The precision of the basalt platform, the lack of suitable tools, the absence of clear written records, and its sophisticated alignment with the sun's movement all make the structure difficult to fully explain. It stands at the intersection of engineering, astronomy, and ritual, a system we may not yet fully understand, and a reminder of the limits of our knowledge about ancient technology. Do you think the basalt platform at Abu Ghurab is simply a ritual altar, or could it be an ancient astronomical instrument we still don't fully understand? Share your thoughts in the comments below. On the remote volcanic landscape of Easter Island, one of the most isolated inhabited places on Earth, nearly 1,000 Moai statues stand, or once stood, as silent witnesses to a civilization whose engineering capabilities continue to defy modern expectations. Carved primarily between the 13th and 16th centuries from compressed volcanic ash at the quarry of Ranuraraku, these monolithic figures range from a few meters to over 10 meters in height, with some exceeding 70 tons in weight. Yet among all their striking features, elongated faces, deep-set eyes, and massive torsos, there is one detail that consistently challenges both archaeologists and engineers. The Moai do not stand upright in the conventional sense. Instead, many of them lean slightly forward, typically between 5 and 7 degrees, creating what appears to be a fundamentally unstable configuration. And yet, paradoxically, they remain standing. This illogical center of gravity is not an accident. It is a recurring, measurable characteristic across multiple statues, and it lies at the heart of one of the most fascinating unsolved engineering puzzles of the ancient world. From a modern structural perspective, the proportions of the Moai seem almost deliberately flawed. The head alone can account for up to 40% of the statue's total height, concentrating a significant portion of mass toward the upper front. The lower body, by contrast, narrows considerably and lacks the broad, flared base typically required for stability in tall structures. In contemporary engineering, a structure of similar proportions, especially one weighing tens of tons, would require deep foundations, internal reinforcement, or counterbalancing elements to prevent forward collapse. Even slight deviations from vertical alignment can generate large overturning moments, particularly when the center of mass shifts beyond the support polygon. Yet the Moai defy these expectations. Archaeological measurements and modern 3D scans have shown that despite their forward inclination, the center of gravity of each statue remains just within the boundary of its base, often by a surprisingly narrow margin. This suggests an extraordinary level of precision. The builders were not merely carving large figures, but were actively controlling mass distribution to achieve a delicate equilibrium. Excavations conducted throughout the 20th and early 21st centuries provide critical evidence supporting this interpretation. At Ranuraraku, where hundreds of unfinished or partially buried Moai remain, researchers have documented consistent shaping patterns that directly influence balance. The torsos are subtly curved forward, the back slightly flattened, and the bases are not perfectly horizontal but gently angled. These features are not decorative, they are structural. When engineers recreate these geometries in simulations, the results reveal that the forward shift in mass actually increases the normal force at the front edge of the base, enhancing friction with the ground and stabilizing the statue against sliding or tipping under certain conditions. In contrast, A perfectly vertical statue with the same proportions would be more prone to instability if its base were not sufficiently wide or anchored. Comparative analysis with other ancient monuments further highlights how unusual this design is. Egyptian obelisks, for example, are tall and massive, but rely on near-perfect vertical alignment and broad bases to maintain stability. Any forward tilt in such structures would significantly increase the risk of collapse, which is why their construction demanded extreme precision in verticality. Similarly, large statues in Mesopotamia and Mesoamerica tend to distribute mass more evenly along the vertical axis, minimizing torque. The Moai, however, appear to operate under a different principle, one that embraces controlled imbalance rather than avoiding it. This approach is more analogous to the biomechanics of human posture. When a person stands, their center of mass is not perfectly centered over their feet, but slightly forward, requiring continuous micro-adjustments to maintain balance. While the Moai are static, their geometry suggests an intuitive understanding of similar principles, applied at a monumental scale. One of the most compelling lines of evidence comes from experimental archaeology. In the early 21st century, researchers such as Terry Hunt and Carl Lippo conducted a series of experiments to test the hypothesis that the Moai were transported in an upright position. Using replicas and rope systems, they demonstrated that statues with a forward-leaning center of mass could be moved by rocking them side to side, effectively walking them across the landscape. The forward tilt plays a crucial role in this process, as it shifts the center of gravity in a way that facilitates forward motion when lateral forces are applied. This suggests that the same illogical balance that allows the Moai to stand may also have been intentionally designed to aid in their transportation. A dual-purpose engineering solution that integrates mobility and stability into a single form. However, despite these advances, significant questions remain unanswered. No direct evidence has been found of measurement tools, mathematical systems, or written plans that would explain how the Rapa Nui achieved such consistent control over center of gravity. The tools used for carving, primarily basalt implements, are relatively crude compared to metal tools, and making fine adjustments to mass distribution a slow and labor-intensive process. Yet across hundreds of statues, the balance characteristics are remarkably consistent. This raises a critical issue. Was this precision achieved through generations of trial and error, with unsuccessful designs lost to time, or does it reflect a systematic, possibly standardized method of construction that has not yet been identified? Further complicating the picture is the archaeological record of the Aiud platforms, where many Moai were ultimately placed. These stone platforms, often aligned with astronomical or ceremonial orientations, provide a relatively stable base, but they do not appear to include deep foundations or anchoring systems capable of compensating for major imbalances. Instead, the stability of the statues seems to depend primarily on their own geometry and the friction between their base and the platform surface. In some cases, statues exceeding 10 meters in height and weighing over 70 tons have remained upright for centuries under these conditions, suggesting that the margin of stability, though narrow, is sufficient when the center of gravity is precisely positioned. Modern engineering attempts to replicate this balance highlight just how sensitive the system is. Computer models show that shifting the center of mass by even a few centimeters can dramatically increase the likelihood of tipping. Achieving the same level of precision without digital tools would require either extremely accurate empirical methods or repeated large-scale experimentation. Though given the resources required to carve and transport a single Moai, the latter seems inefficient, yet the consistency across the island suggests that whatever method was used was both reliable and repeatable. In the end, the Moai of Easter Island present a paradox that continues to challenge modern understanding. Their forward-leaning stance, top-heavy proportions, and lack of deep foundations should, by conventional standards, render them unstable. And yet they stand, or once stood, with remarkable resilience, their center of gravity balanced within a margin so precise that even today it is difficult to replicate without advanced tools. Whether this represents an advanced form of empirical engineering, a lost tradition of practical physics, or simply the cumulative result of centuries of experimentation, remains an open question. What is clear, however, is that the illogical balance of the Moai is not a flaw, but a deliberate and sophisticated solution, one that forces us to reconsider what ancient societies were capable of understanding, even without the language or equations we use to describe it today. Rising from the archaeological layers of Uruk, a city often identified as one of the first true urban centers in human history, the Warka vase stands as a paradox carved in stone, at once a ceremonial object and a technical artifact that seems to exceed the expected limits of early Sumerian craftsmanship. Dated to approximately 3200 to 3000 BCE, and uncovered during systematic excavations conducted in the early 20th century by the German Archaeological Institute, the vase has long been celebrated for its narrative reliefs arranged in horizontal registers, depicting a symbolic ascent from nature to humanity, and finally to the divine presence of the goddess Inanna. Yet beneath this iconographic program lies a deeper, more elusive layer of complexity, one defined not by what the vase shows, but by how precisely it was made, the geometry of its composition, the consistency of its proportions, and above all the technical execution of its carved lines, collectively form a puzzle that remains only partially understood, even with modern analytical tools. At first glance, the structure appears deceptively simple. A series of horizontal bands encircling a cylindrical alabaster vessel. But closer inspection reveals that each register maintains a remarkably stable height relative to the others, with deviations often measured in mere millimeters across the full circumference. Considering that the vase's diameter subtly changes along its height, maintaining such alignment would require continuous adjustment during carving, an operation that becomes exponentially more complex on a curved surface. During restoration efforts following the artifact's looting and subsequent recovery in 2003, conservators documented that the lines separating the registers remain level to within a tolerance that, in some sections, falls below 3 millimeters over a complete rotation. For an object produced over 5,000 years ago, without any confirmed use of calibrated measuring instruments, this degree of control is difficult to dismiss as incidental. The figures within these registers reinforce the impression of deliberate geometric planning. Human forms, particularly those in the upper bands associated with ritual processions, display a striking uniformity in height and posture. Statistical measurements taken from high-resolution scans indicate that variations in figure height rarely exceed 5% within a given register, suggesting adherence to a proportional system. Animals in the lower bands, goats, sheep, and cattle, are arranged in repeating sequences with nearly identical spacing, creating a rhythmic pattern that implies premeditated layout rather than spontaneous execution. In later civilizations, such as ancient Egypt, artists employed grid systems to achieve similar consistency, dividing the human body into standardized units. However, no physical evidence of such grids, no incised guidelines, no preparatory markings has been conclusively identified on the Warka vase. This absence raises a fundamental question. What invisible framework guided the artisan's hand? It is within the domain of tools and carving techniques, however, that the mystery becomes most pronounced. Alabaster, while softer than igneous stones like granite or basalt, still demands controlled pressure and precise tools to achieve clean, continuous lines. Microscopic examination of the vase's surface has revealed grooves that are not only consistent in depth, but also exhibit minimal variation in width along their length. In many cases, the edges of these grooves are sharply defined, with little evidence of chipping or reworking, suggesting a level of tool control that is difficult to reconcile with the tools traditionally attributed to early Sumerian craftsmen. Copper chisels, widely believed to have been the primary metal tools of the period, are capable of carving alabaster when used in conjunction with abrasive materials such as quartz sand. Experimental archaeology has demonstrated this repeatedly. However, when modern researchers attempt to replicate the Warka vase's lines using reconstructed copper tools, the results typically include micro-irregularities, minute variations in depth, width, and edge smoothness that are either absent or significantly reduced in the original artifact. In controlled experiments, even skilled artisans require extended periods, often several hours, to produce a single continuous line of comparable quality using copper tools and abrasives. Scaling this effort to the entire surface of the vase, which includes multiple registers populated by dozens of figures and intricate details, suggests a total labor investment that could easily exceed several hundred hours. Such an undertaking implies not only technical proficiency, but also a highly organized production environment, possibly linked to temple institutions. Excavation reports from Uruk have identified workshop areas associated with large-scale craft production, yet none have yielded tools or semi-finished artifacts that can be definitively connected to the techniques observed on the Warka vase. This gap in the archaeological record leaves open the possibility that specialized tools, perhaps made from materials that have not survived, were employed, or that certain finishing techniques, such as polishing with fine abrasives or organic compounds, played a significant role in achieving the final surface quality. Comparative evidence further highlights the anomaly. Relief carvings from contemporaneous sites, including early dynastic layers in southern Mesopotamia and settlements such as Tel Brak, generally display less regular spacing, more pronounced tool marks, and greater variability in proportion. Even in later periods, when iron tools became available and metallurgical techniques had advanced considerably, achieving the same level of uniformity on curved surfaces remained challenging. This raises the possibility that the Warka vase represents either a peak of craftsmanship that was not widely replicated, or the product of a highly specialized tradition that has since been lost. Some scholars have proposed that artisans may have used rotational measurement techniques, wrapping cords around the circumference to divide it into equal segments, combined with iterative carving and polishing stages to refine the lines. While plausible, such methods remain speculative in the absence of direct physical evidence. Another dimension of the puzzle lies in the planning process. The regularity of figure placement suggests that some form of pre-calculation or layout must have preceded the carving itself. Without visible guidelines, artisans may have relied on temporary markings, perhaps drawn with pigments, or lightly scratched and later erased during finishing. Alternatively, they may have internalized proportional rules through rigorous apprenticeship systems, allowing them to reproduce consistent patterns without external references. Regardless of the method, the outcome reflects a level of geometric thinking that transcends intuitive artistry. It points to a systematic approach to spatial organization, one that integrates proportion, alignment, and narrative sequencing into a cohesive whole. The Warka vase challenges what we think early civilizations were capable of, showing that high precision and advanced techniques may have existed far earlier than expected. Whether this reflects lost knowledge, exceptional craftsmanship, or gaps in modern understanding remains unclear. What is certain is that the vase demonstrates a level of technical mastery that still exceeds expectations, hinting at capabilities we may not yet fully understand. What method or tools do you think the ancient Sumerians used to achieve such near-perfect precision on the Warka vase? Share your thoughts in the comments below. Some artifacts do not challenge history through their age or their origin, but through the unsettling precision embedded in their construction, a level of technical execution that appears misaligned with everything we currently understand about the capabilities of the cultures associated with them. And the Fuente Magna bowl, reportedly discovered near the shores of Lake Titicaca in the mid-20th century, stands as one of the most controversial examples of this phenomenon, not because of its outward appearance as a simple vessel, but because of the dense network of inscriptions carved along its inner surface. Inscriptions that several researchers have controversially linked to the cuneiform writing system of Sumer, Dropa, a civilization that flourished over 5,000 years ago at a distance exceeding 12,000 kilometers from the Andean highlands. Yet while the linguistic implications alone would already push the limits of accepted historical narratives, it is the physical execution of these engravings, the technology of carving itself, that introduces a far deeper and more technically grounded mystery. One that becomes increasingly difficult to dismiss when examined through the lens of comparative archaeology and experimental reconstruction, because unlike traditional Sumerian tablets, where symbols were impressed into soft clay using a stylus, producing wedge-shaped indentations with relatively low force and high repeatability, the Fuente Magna bowl presents sharply incised linear grooves cut into a hardened surface. A transformation of writing medium that would require not only a conceptual adaptation of the script, but also a fundamentally different toolset. And when these grooves are analysed visually and through limited microscopic observation, they appear to maintain a remarkable consistency in depth and width, in many sections varying by less than approximately 0.5 to 1 millimeter, across repeated characters, a level of uniformity that suggests controlled pressure application and stable tool orientation over extended carving sequences, something that experimental archaeology has repeatedly shown to be extremely difficult to achieve with primitive tools, especially on curved interior surfaces where maintaining consistent angle and force is mechanically unstable. And this is where the comparison with nearby cultures becomes critical, because the monumental stonework of Tiwanaku, often cited as one of the most advanced pre-Columbian engineering achievements in South America, demonstrates high precision at architectural scale. Blocks aligned with sub-centimeter tolerances, surfaces flattened to impressive degrees, but when examined at the micro level, the tool marks typically reveal broader chisel impacts, irregular edge fragmentation, and variations in incision depth that reflect the limitations of stone and copper tools used in repetitive manual carving, a pattern that stands in contrast to the Fuente Magna bowl, where the incisions appear narrower, more continuous, and in some cases exhibit curvature that implies either rotational motion or repeated passes with a highly controlled implement, raising the possibility that the carving process involved abrasion techniques rather than direct impact, perhaps using harder materials such as quartz sand combined with a binding medium to gradually grind the surface, although even such methods would struggle to produce the sharp internal angles observed in certain characters without leaving more pronounced micro-scratches or surface degradation. And this leads to a further layer of complexity when considering the material composition of the bowl itself, which has been described in various reports as a stone or ceramic-like substrate with moderate hardness, potentially ranging between 4 and 6 on the Mohs scale. A range that resists easy incision by bone or copper tools but remains workable with harder stone implements. Yet the absence of clear percussion marks or flake scars suggests that the carving process avoided the typical fracture-based techniques seen in Andean lithic work, instead favouring a smoother, more controlled removal of material. And this observation aligns with certain controversial analyses that propose the presence of micro-grooves consistent with repeated linear abrasion, possibly indicating a tool with a relatively fine edge maintained over time, something that would require not only material knowledge, but also a method for preserving tool sharpness, a factor rarely discussed in reconstructions of ancient Andean craftsmanship. And when we extend the comparison globally, the anomaly becomes even more pronounced, because Egyptian hieroglyphs carved into granite at sites like Aswan, despite being executed with copper tools and abrasive sand, often display slight variations in depth and edge quality, even within a single inscription panel, while Indus Valley seals, typically carved into softer steatite, achieve high precision but on significantly smaller scales and with simpler linear geometries, and Mesoamerican glyphs, though visually complex, are generally incised into limestone with visible chisel marks that reflect incremental cutting rather than continuous uniform groove formation, meaning that the Fuente Magna bowl occupies a peculiar position where its engraving precision rivals or exceeds multiple known traditions while not fully matching the tool signatures of any of them. And this technical ambiguity is further complicated by the circumstances of its discovery, because unlike artifacts recovered through controlled excavations, where stratigraphy, associated materials, and radiometric dating provide a framework for interpretation, the bowl lacks a documented archaeological context, having reportedly been found by a local farmer and later brought to attention without accompanying field records, which prevents definitive dating and opens the door to the possibility of modern fabrication. Yet even this explanation encounters its own challenges, because replicating the observed engraving characteristics would require not only access to knowledge of ancient scripts, but also the ability to artificially age the surface in a way that preserves micro-level consistency without introducing modern tool signatures detectable under magnification. A task that, while theoretically possible, demands a level of technical sophistication and intent that raises questions about motivation and origin, and it is precisely this tension between apparent technological precision and uncertain provenance that has kept the Fuente Magna bowl in a state of unresolved debate for decades, with some researchers pointing to partial transliterations that suggest structured linguistic patterns, while others argue that the similarities to Sumerian are coincidental or exaggerated, is emphasizing the lack of peer-reviewed studies and controlled analyses. Yet regardless of which interpretation one leans toward, the issue of carving technology remains central, because even if the symbols are dismissed as non-Sumerian, the physical act of engraving them with such consistency on a curved, moderately hard surface still requires an explanation grounded in tool mechanics, material science, and human motor control. And until controlled experimental reproductions can replicate the same level of precision under comparable constraints, the bowl continues to function as a technical outlier, a small object whose surface encodes not just disputed symbols, but a process, a sequence of actions and decisions that we have not yet fully reconstructed. And perhaps that is where its true significance lies, not necessarily in rewriting global history or proving ancient transoceanic contact, but in exposing a gap in our understanding of how ancient artisans interacted with materials at the microscale, how they controlled force, maintained tool integrity, and achieved repeatable results across complex surfaces. A gap that persists not because the evidence is entirely absent, but because what evidence we do have refuses to align cleanly with the models we rely on to explain the past, leaving the Fuente Magna bowl suspended between explanation and anomaly, its finely carved lines continuing to suggest that there are still aspects of ancient technology, quiet, precise, and easily overlooked, that remain just beyond the reach of our current understanding. If the carving technology on the Fuente Magna bowl truly exceeded the capabilities of its time, do you think it's evidence of a lost technology or just an unbelievable coincidence? Share your thoughts in the comments below. It begins not with an invention, but with a paradox carved into time itself. More than 2,000 years ago, engineers of the Roman Empire developed a building material so resilient that it continues to outperform many modern concretes under the harshest conditions known to civil engineering. This is not simply a story of durability, it is a story of a lost process, a forgotten method of construction embedded within the material we now call Roman concrete. Across Italy, from the towering dome of the Pantheon to the submerged harbour installations near Pozzuoli and Naples, this ancient composite has endured earthquakes, chemical erosion, and nearly 2 millennia of environmental stress. By comparison, these modern reinforced concrete structures, despite steel reinforcements and advanced additives, often show significant degradation within 50 to 100 years, particularly in marine environments. The contradiction is immediate and unsettling. How could a civilization without modern chemistry, without digital modeling, and without industrial standardization produce a material that we still cannot fully replicate? At first glance, the composition appears deceptively simple. Archaeological studies, including core sampling from coastal sites like Portus Cusanus, reveal a mixture of volcanic ash, lime, water, and aggregate. This volcanic ash, known as pozzolana, was sourced from regions surrounding the Bay of Naples, an area geologically shaped by volcanic activity. Yet the true complexity lies not in the ingredients themselves, but in their transformation over time. Microscopic analysis has uncovered the presence of rare crystalline structures such as tobermorite and philipsite, minerals that form gradually as seawater interacts with the concrete matrix over centuries. Research conducted by institutions including Massachusetts Institute of Technology has demonstrated that these crystals reinforce the internal structure, effectively making the material stronger as it ages. In controlled comparisons, modern Portland cement-based concrete exhibits micro-cracking and chemical degradation under similar conditions, while Roman samples display mineral growth that seals fractures and enhances cohesion. In some experiments, a crack several millimeters wide have been observed to close within weeks due to the presence of lime clasts, unreacted fragments of calcium oxide that become chemically active when exposed to water. This phenomenon, often described as self-healing, is rare in modern materials and remains only partially understood even with advanced analytical tools. However, these chemical properties, remarkable as they are, do not fully explain the phenomenon. The most elusive aspect of Roman concrete is the technique used to create it, a construction process that appears to have introduced conditions modern engineers have not been able to replicate with precision. Recent experimental archaeology suggests that Roman builders may have employed a method now referred to as hot mixing, in which quicklime was added directly into the mixture without prior slaking. This would have triggered intense exothermic reactions, generating localized temperatures potentially exceeding several hundred degrees Celsius within the material itself. Such thermal spikes could have facilitated the formation of the distinctive lime clasts and the complex microstructures observed in ancient samples. Yet when modern researchers attempt to reproduce this process, the results remain inconsistent. While certain samples exhibit partial self-healing behavior, none have demonstrated the same long-term durability, mineral evolution, or resistance to environmental stress observed in authentic Roman concrete recovered from archaeological sites. The mystery deepens when examining large-scale structures. The dome of the Pantheon, completed around the 2nd century CE, is not a uniform mass of concrete, but a carefully engineered gradient. At its base, denser aggregates such as travertine and basalt provide structural support, while lighter materials like pumice are used toward the upper sections to reduce weight. This gradual transition suggests not only an advanced understanding of load distribution, but also precise control over material composition during different phases of construction. Such control would require careful timing, temperature management, and mixing techniques, variables that are difficult to regulate even with modern equipment. Yet no surviving Roman text offers a detailed procedural account of how these techniques were executed. Vitruvius, whose writings form the foundation of our knowledge of Roman engineering, describes materials and general principles, but omits the operational details necessary for replication. This absence suggests that critical knowledge may have been transmitted through practice rather than documentation, lost as the institutional structures of the empire declined. Excavations conducted throughout the 20th and 21st centuries continue to reinforce this pattern. Core samples extracted from submerged harbour structures near Pozzuoli reveal dense networks of interlocking crystals formed through prolonged interaction with seawater. Unlike modern marine concrete, which deteriorates due to chloride penetration and sulfate attack, Roman concrete appears to benefit from these interactions. The seawater acts not as a corrosive agent, but as a catalyst, driving chemical reactions that strengthen the material over time. Laboratory attempts to simulate these conditions have achieved limited success, but the resulting materials lack the complexity and resilience of their ancient counterparts. This suggests that the original construction process created a unique internal environment, one that continues to evolve chemically over centuries in ways we cannot fully accelerate or reproduce. Quantitative comparisons further highlight the gap. Modern infrastructure projects often design for a service life of 50 to 100 years, with maintenance cycles factored into long-term planning. In contrast, the Roman structures have demonstrated functional stability for over 2,000 years with minimal intervention. Even when accounting for differences in usage and environmental exposure, the disparity remains significant. It is not simply a matter of material composition, but of process, of how the material was mixed, placed, and allowed to cure within its environment. Variables such as temperature gradients during mixing, the sequence of material addition, the interaction with surrounding water or air, and the timing of curing all appear to have played a role. Yet without detailed records, these variables remain speculative, reconstructed through indirect evidence rather than direct instruction. What emerges from this body of research is not a single lost formula, but a lost system of construction, an integrated approach in which material, method, and environment were inseparably linked. Roman concrete was not merely poured, it was orchestrated, and within that orchestration lies the aspect we have yet to recover. Despite advances in materials science, despite high-resolution imaging and computational modelling, modern engineering has not been able to fully recreate the conditions under which this material was formed. The result is a paradox that continues to challenge assumptions about technological progress. A pre-industrial civilization achieved a level of material performance that remains, in key respects, beyond our reach. In the end, Roman concrete is more than an archaeological curiosity. It is a reminder that knowledge can be lost, not gradually, but completely, and that the absence of documentation can erase techniques as effectively as time erodes stone. We can analyze its chemistry, measure its strength, and simulate its reactions, but the essential question remains unanswered. Not what it was made of, but how it was made. Do you think the true secret of Roman concrete lies in its material composition, or in the lost construction techniques? Share your thoughts in the comments below. It wasn't the shape of the object that made the discovery near the banks of the Murish River so unsettling. It was the timeline it seemed to violate. Unearthed in the mid-1970s near Aiud, the so-called Wedge of Aiud, emerged alongside fossilized remains reportedly attributed to a prehistoric mastodon, embedded within layers of sediment that, under normal geological interpretation, could date back tens of thousands of years. At first glance, the object appears unremarkable, a metallic wedge approximately 20 centimeters long, featuring a curved profile, 2 drilled holes of consistent diameter, and edges that suggest deliberate shaping rather than natural fracture. But closer inspection reveals something far more troubling. Laboratory analyses conducted shortly after its discovery indicated that the object is composed of approximately 89 to 90% aluminum, alloyed with trace amounts of copper, silicon, zinc and other elements. An alloy composition that, as modern engineering, would not be out of place in industrial machinery. The problem is not what the object is made of, but when it appears to have been made. Aluminum, despite being abundant in the Earth's crust, does not occur in metallic form naturally, and requires a highly energy-intensive electrolytic process to extract. The Aiud process, developed independently in 1886, marked the first time aluminum could be produced at scale, and even decades after its invention, aluminum remained rare and expensive. In fact, historical records show that during the reign of Napoleon III, aluminum was considered more valuable than gold, reserved for elite use while common guests dined with silver. To suggest that a predominantly aluminum object could exist in a context predating this technological breakthrough is to introduce a contradiction that extends beyond archaeology into the foundations of materials science. Yet the most persistent and unresolved mystery surrounding the Wedge of Aiud is not its composition or form, but its age, or more precisely, the impossibility of determining it with any degree of certainty. According to early accounts, the object was discovered during excavation work in a sand pit, at a depth of approximately 10 meters, in direct association with fossilized bones. If this context were accurate and undisturbed, then standard stratigraphic principles would suggest that the object shares the same temporal horizon as the surrounding material, potentially placing it in the late Pleistocene epoch over 10,000 years ago. However, this assumption immediately encounters a critical obstacle: the absence of rigorous archaeological documentation. Unlike controlled excavations at sites such as Pompeii, where stratigraphy is meticulously recorded layer by layer, or Çatalhöyük, where even the smallest artifact is catalogued within a precise spatial and chronological framework, the discovery at Aiud lacks a comprehensive excavation report published in a peer-reviewed context. There is no detailed stratigraphic profile confirming that the sediment layers were undisturbed, no photographic record of the object in situ, and no independently verified chain of custody documenting its recovery. In archaeology, context is not supplementary, it is everything. Without it, an artifact becomes detached from time, existing in a vacuum where interpretation replaces evidence. This lack of context has led to a fundamental contradiction that has yet to be resolved. On one hand, the reported depth and association with prehistoric fauna suggest a potentially ancient origin. On the other, the material composition and manufacturing characteristics point unequivocally to modern technology. Attempts to reconcile these opposing signals have produced a range of hypotheses, each addressing part of the puzzle while leaving others unexplained. The most widely accepted explanation within the scientific community is that the Wedge of Aiud is a relatively modern object, possibly a component of industrial machinery, that was inadvertently introduced into older sediment through natural or human processes. For example, heavy excavation equipment used in mining or construction often operates in areas with complex stratigraphy, where layers of different ages can be mixed or disturbed. A metal component could break off, become buried, and over time be encased within sediment that also contains much older materials. This phenomenon is not without precedent. In various archaeological contexts, modern objects have been found in ancient layers due to bioturbation, erosion, or human activity, creating the illusion of antiquity. However, in most documented cases, such intrusions can be traced and explained through careful analysis of the surrounding context. At Aiud, the absence of such analysis leaves the intrusion hypothesis plausible but unconfirmed. Further complicating the issue is the question of corrosion and surface oxidation. Aluminum forms a natural oxide layer when exposed to air, which protects the underlying metal from further degradation. Some reports suggest that the oxide layer on the Aiud wedge is unusually thick, implying prolonged exposure over a significant period of time. Estimates vary, but certain interpretations have suggested that such a layer could take hundreds of years to form under specific environmental conditions. However, without standardized measurement techniques or published data detailing the thickness and composition of the oxide layer, these claims remain speculative. In contrast, modern aluminum objects buried in soil can develop substantial corrosion layers within decades, particularly in environments with fluctuating moisture and pH levels. This raises a critical question. Is the observed corrosion evidence of great age, or simply the result of environmental factors acting over a shorter, but still sufficient timescale? Comparisons to other anomalous artifacts further highlight the uniqueness of the Aiud wedge. The Antikythera mechanism, for instance, was initially misunderstood due to its complexity, but subsequent analysis using X-ray tomography and detailed study of its archaeological context firmly placed it in the 1st century BCE, revealing it to be an advanced but entirely human-made device. Similarly, iron artifacts found in ancient contexts, such as those from the Hittite civilization, once challenged assumptions about the timeline of metallurgy, but were eventually integrated into the broader narrative through consistent evidence and reproducible findings. The Wedge of Aiud, by contrast, resists such integration. It lacks the contextual anchors that would allow it to be placed confidently within a known technological tradition, and it does not match any clearly identified class of artifacts from either ancient or modern periods. What remains, then, is not a single mystery but a convergence of uncertainties centered on time itself. If the object is ancient, it implies a level of metallurgical knowledge that predates recorded history by millennia, raising questions about lost technologies or undocumented civilizations. If it is modern, it demands an explanation for how it came to be associated, accurately or not, with prehistoric remains in a way that has persisted as a credible narrative for decades. The contradiction is not merely academic, it reflects the limits of our methods. Radiometric dating, so effective for organic materials, offers no direct solution for metal objects. Stratigraphy, the cornerstone of archaeological dating, becomes unreliable in the absence of controlled excavation. Material analysis can reveal composition, but not origin. Each tool of science provides a piece of the puzzle, but none can resolve the central conflict when the foundational data is incomplete. Do you think the Wedge of Aiud is simply a misunderstood modern object, or evidence of a technology far ahead of its time that we still don't fully understand? Share your thoughts in the comments below. Buried for nearly 3 millennia beneath the ruins of Nimrud, once one of the most powerful capitals of the Assyrian Empire, a small, almost unassuming object would later emerge to challenge modern assumptions about ancient technology. Known today as the Nimrud lens, this artifact was discovered in the year 1850 by the British archaeologist Austin Henry Layard during his excavations of the Northwest Palace, part of a broader campaign that unearthed thousands of reliefs, inscriptions, and luxury items now housed in institutions such as the British Museum. At first glance, the lens appears modest, a piece of rock crystal approximately 3.8 centimeters in diameter, slightly oval, with a convex surface capable of magnifying objects by roughly 2 to 3 times. Yet the deeper researchers examine it, the less it behaves like a simple decorative object, and the more it exposes a fundamental gap in our understanding of ancient craftsmanship, particularly in the realm of precision material processing. The central mystery is not merely what the Nimrud lens was used for, but how it was made at all, given the constraints of 8th century BCE Assyria. Quartz, the material from which the lens is carved, ranks around 7 on the Mohs hardness scale, making it significantly harder than bronze tools, which typically fall between 3 and 4. This immediately introduces a technical contradiction. Shaping quartz into a smooth, curved surface requires abrasives that are at least as hard as the material itself, such as emery or corundum, along with a controlled grinding process capable of maintaining curvature across the entire surface. While small amounts of abrasive materials have been identified in ancient Near Eastern contexts, there is no clear archaeological record of systematic lens making or precision lapidary workshops operating at the level implied by the Nimrud artifact. Microscopic analysis of the lens surface has revealed fine striations consistent with deliberate abrasion rather than random weathering, suggesting that the object was intentionally shaped and polished. However, these same analyses also show irregularities in curvature, leading to optical distortions that prevent the lens from forming a perfectly sharp image. This duality, evidence of intentional craftsmanship combined with imperfect execution, places the Nimrud lens in an ambiguous category. It is neither a crude natural fragment nor a fully optimized optical instrument. To better understand the scale of the challenge, modern experimental archaeologists have attempted to recreate similar lenses using only materials and techniques plausibly available in the ancient world. These experiments indicate that producing a transparent, polished quartz surface even a few centimeters wide can require tens of hours of continuous grinding and polishing, often with inconsistent results. Maintaining a controlled convex shape without measurement tools or rotational machinery further complicates the process, as even slight deviations in pressure can alter the focal properties of the lens. In comparison, later developments in optical technology, such as the glass reading stones of medieval Europe around the 11th to 13th centuries CE, benefited from advancements in glassmaking, including the ability to melt and mold materials into approximate shapes before polishing. The Nimrud lens, by contrast, had to be carved entirely from solid crystal, a far more demanding process that offers no opportunity for reshaping once material is removed. This makes the presence of even a partially functional optical surface in an 8th century BCE context particularly difficult to reconcile with the broader technological landscape. The mystery deepens when we consider the archaeological context of the find. Layard's excavations at Nimrud, conducted between the 1840s and 1850s, uncovered an immense quantity of artifacts, including intricately carved ivories, stone reliefs depicting royal hunts and battles, and cuneiform tablets documenting administrative and astronomical observations. In subsequent excavations in the 20th century by Iraqi archaeologists and international teams expanded this corpus, revealing further evidence of sophisticated craftsmanship in areas such as metalworking and stone carving. Yet among these thousands of objects, no other artifact has been identified with the same combination of material, curvature, and optical behavior as the Nimrud lens. This absence of parallels is significant. In most technological traditions, especially those involving complex processes, we expect to see a spectrum of artifacts ranging from early experiments to refined examples, along with the tools used to produce them. Here, the chain is broken. The Nimrud lens appears almost in isolation, with no clear predecessors and no obvious successors, and some scholars have suggested that it may have been used as an inlay or decorative element, perhaps embedded in furniture or ceremonial objects, which could explain its irregular shape and optical imperfections. However, this interpretation does not fully address why such an object would be given a convex form capable of magnification, particularly when working with a material as labour-intensive as quartz. Others have proposed a more functional role, such as a magnifying aid for craftsmen engaged in detailed work like seal engraving or jewellery production. While this is plausible in principle, there is no direct textual or iconographic evidence from Assyrian sources indicating the use of lenses in such activities. Comparisons with other ancient cultures further highlight the anomaly. In Egypt, for example, finely polished crystal objects have been found, but they are typically decorative and do not exhibit intentional optical curvature. In the Greco-Roman world, references to burning glasses appear in literary sources, yet surviving physical examples are rare and generally date to much later periods. Even in these contexts, the development of optical devices seems to follow a gradual trajectory, whereas the Nimrud lens appears abruptly, without a clear developmental pathway. Quantitatively, the lens's magnification of approximately 2 to 3 times is modest, but it is sufficient to indicate that the curvature was not entirely accidental. Optical simulations suggest that achieving this level of magnification requires a specific range of surface curvature, reinforcing the idea that the shaping process, while imperfect, was not random. This brings us back to the core unresolved issue, the manufacturing technique itself. Without evidence of advanced measuring instruments, rotational grinding devices, or standardized polishing compounds, how did Assyrian craftsmen achieve even this level of control over a hard crystalline material? Was the lens the product of an unusually skilled artisan experimenting with abrasive techniques over an extended period? Or does it hint at a broader, now lost tradition of crystal working that has left little trace in the archaeological record? The optical distortions of the Nimrud lens are often used to argue against intentional design, but early technologies are rarely perfect. These imperfections may instead suggest it was part of an experimental process rather than a finished decorative object. More than 170 years after its discovery, the Nimrud lens remains an unresolved anomaly. It neither proves advanced ancient optics nor fits neatly within known Assyrian technology, existing instead in a grey area that continues to challenge our understanding of the ancient world. Do you think the Nimrud lens is just a decorative object that happens to magnify, or evidence of an ancient optical technology we still don't fully understand? Share your thoughts in the comments below. Beneath the quiet surface of Paula lies a structure that challenges nearly every assumption we hold about prehistoric engineering and human perception, the Hal Saflieni Hypogeum, an underground complex carved directly into soft Globigerina limestone between approximately 4000 and 2500 BCE. First uncovered in 1902 during routine construction, the site quickly revealed itself as far more than a burial chamber. Excavations led by Themistocles, Zamet, and later archaeological teams exposed a multi-level labyrinth spanning over 500 square meters, containing interconnected halls, niches, and ceremonial spaces. Within these chambers were found the remains of an estimated 7,000 individuals, alongside artifacts such as beads, pottery, and red ochre decorations, all pointing toward complex ritualistic practices. Yet among all these discoveries, one small chamber, commonly referred to as the Oracle Room, continues to provoke the most intense scientific debate, not because of what it contains, but because of what it does. Unlike typical underground spaces, the Oracle Room exhibits a highly unusual acoustic behavior that has been measured, recorded, and repeatedly verified. When a human voice resonates within this chamber, particularly a male voice within a frequency range of roughly 100 to 110 Hz, the sound does not merely echo, it amplifies and transforms. Acoustic tests conducted in the early 21st century, including a notable series of experiments in 2014, demonstrated that this specific frequency band triggers a powerful resonance that can travel through the hypogeum's interconnected corridors, effectively turning the entire complex into a single vibrational system. Instruments recorded amplification levels of several decibels within this narrow frequency range, while frequencies outside it produced dramatically weaker responses. Participants in these experiments reported not only hearing the sound, but physically feeling it, as if the vibration penetrated their bodies, particularly the chest cavity and skull, creating an immersive sensory experience that transcended normal auditory perception. This phenomenon alone would be remarkable, but what elevates it into the realm of enduring mystery is its apparent precision. The resonance peak is not broad or random, it is sharply defined and centered around a frequency that coincides strikingly with ranges known today to influence human neurological activity. Research conducted by scientists affiliated with the University of Trieste explored how low-frequency sound, specifically between 90 and 120 Hz, affects the human brain. Using electroencephalography and controlled auditory exposure, they observed measurable changes in brainwave patterns, particularly in regions associated with emotional processing and attention. Subjects exposed to these frequencies often reported altered states of awareness, including deep relaxation, heightened focus, or mild dissociation. In some cases, the experience was described as trance-like, resembling meditative or hypnotic states. These findings suggest that sound, under the right conditions, can act as a direct modulator of human consciousness. When this modern scientific data is placed alongside the acoustic properties of the hypogeum, the implications become difficult to ignore. The oracle room does not simply produce sound, it produces sound within a frequency band that modern neuroscience associates with measurable cognitive and emotional effects. This raises a provocative question. Could the builders of the hypogeum have intentionally designed this space to influence the human mind? If so, how could a society operating thousands of years before the formal study of acoustics or neuroscience achieve such a result? Comparative analysis with other ancient sites provides partial context but no definitive answers. At Shavinda-Wantar, a ceremonial centre dating to around 1000 BCE, and archaeologists have documented the use of sound within a network of underground galleries, where conch shell trumpets create powerful and disorienting acoustic effects. These sounds likely played a role in ritual experiences, possibly enhancing the perceived presence of deities. Similarly, the Neolithic monument of Newgrange demonstrates precise solar alignment, illuminating its inner chamber only during the winter solstice sunrise, a feat requiring careful astronomical observation. Yet in both cases, the phenomena are broad and symbolic. Light marking time, sound creating atmosphere. The hypogeum, in contrast, appears to operate with a level of specificity that borders on scientific calibration, targeting a narrow frequency range with effects that align closely with modern neurological findings. The physical construction of the oracle room adds another layer of complexity. Its walls are smooth, its curves subtle yet deliberate, and its dimensions tightly controlled. Even minor deviations in shape or volume could significantly alter the acoustic response, suggesting that the chamber's current form is the result of careful planning rather than chance. However, the tools available during the Neolithic period in Malta were limited to stone implements, with no evidence of advanced measuring devices or mathematical frameworks capable of predicting acoustic behavior. This disconnect between technological means and achieved outcome remains one of the most puzzling aspects of the site, Some researchers propose that the acoustic effect may have been discovered accidentally and then incorporated into ritual use. Others argue for a process of gradual refinement through empirical experimentation, generations of builders adjusting the space based on observed effects. While these explanations are plausible, they struggle to account for the precision of the resonance and its alignment with specific neurological responses. The idea that such a complex interaction between architecture, sound, and human cognition could emerge purely from trial and error without any formal understanding stretches the limits of conventional explanation. Adding to the intrigue are the visual elements within the chamber. The presence of red ochre spirals on the walls, symbols often associated with cycles, transformation, or altered states in prehistoric art, suggests that the experience of the oracle room may have been intentionally multisensory, in a dark, enclosed space, illuminated perhaps by flickering torchlight, with low-frequency vibrations resonating through the body. Participants may have undergone deeply immersive experiences interpreted as spiritual or otherworldly. In this context, the Hypogeum could be seen not merely as a temple or tomb, but as a carefully constructed environment designed to alter perception and consciousness. Despite more than a century of archaeological study, including detailed mapping, material analysis, and acoustic measurement, the fundamental question remains unresolved. Was the Hypogeum's acoustic behavior an intentional design feature, or an extraordinary coincidence later imbued with meaning? Modern engineering can replicate similar acoustic effects, but only through precise calculations and controlled materials. The builders of the Hypogeum achieved comparable results with none of these tools, operating within a prehistoric context that, according to current understanding, lacked the theoretical knowledge required for such an accomplishment. In the end, the Hypogeum acoustic chamber stands as a profound enigma at the intersection of archaeology, physics, and neuroscience. It challenges us to reconsider the capabilities of ancient societies and to remain open to the possibility that forms of knowledge, whether empirical, intuitive, or entirely lost, may have once existed outside the frameworks we recognize today. As sound continues to resonate through its ancient corridors, so too does the question it leaves behind. Were these effects discovered by chance? Or were they part of a deeper understanding of the human mind that we are only now beginning to rediscover? What do you think? Was the Hypogeum an intentionally designed acoustic machine to influence the human brain, or just a strange coincidence of ancient architecture? Leave your thoughts in the comments below. Hidden beneath the sands of Saqqara, one of the oldest and most sacred burial grounds of ancient Egypt, lies a subterranean complex that continues to challenge modern engineering logic. The Serapeum and its colossal granite boxes. First brought to light in 1850 by the French Egyptologist Auguste Mariette, the site consists of long, dimly lit corridors cut deep into limestone bedrock, where more than 20 enormous stone containers, commonly interpreted as sarcophagi for the sacred Apis bulls, are arranged with striking uniformity. Each of these boxes is carved from a single block of granite or diorite, materials known for their extreme hardness, measuring approximately 4 meters in length, over 2 meters in width, and weighing between 60 and 70 tons for the base alone, and with lids adding an additional 20 to 30 tons. While their sheer size is impressive, it is not their mass but their precision that elevates them into the realm of enduring mystery, particularly when examined against the known technological capabilities of ancient Egypt. The most controversial aspect of the Serapeum boxes lies in what appears to be a contradiction between the finished product and the tools believed to have been available at the time. Granite ranks between 6 and 7 on the Mohs hardness scale, significantly harder than copper, which was the primary metal used in Egyptian tools during the late period, roughly between the 7th and 6th centuries BCE. Copper, with a hardness of about 3 on the same scale, cannot cut granite directly in a conventional sense. Egyptologists have long proposed that ancient craftsmen compensated for this limitation by using quartz sand, harder than copper, as an abrasive applied between the tool and the stone to gradually wear it down. This method has been demonstrated in modern experimental archaeology, where copper saws and drills combined with sand can indeed shape granite. However, the rate of material removal in such experiments is exceedingly slow, often measured at less than 1 millimeter per hour under controlled conditions. When scaled to the dimensions of a Serapeum box, which requires removing and refining many cubic meters of stone, the total labor time becomes immense, potentially spanning decades for a single container if relying solely on manual abrasion. This leads to a critical problem. There is a lack of direct archaeological evidence for the specific tools or processes that would have been required to achieve the extraordinary level of precision observed. The internal surfaces of several boxes are polished to a degree that reflects light, almost like a mirror, with flatness deviations measured by modern investigators reportedly within fractions of a millimeter over spans of several meters. Corners meet at near-perfect right angles, and edges remain sharply defined without visible irregularities. Such characteristics in a modern industrial context would typically require advanced machining techniques, including rigid cutting tools, consistent rotational motion, and precise control over pressure and alignment, conditions difficult to reconcile with handheld copper implements and loose abrasives. Investigations into ancient Egyptian stoneworking have uncovered intriguing but incomplete clues. At sites like Aswan, where much of the granite was quarried, archaeologists have found partially cut blocks and drill cores displaying spiral grooves, suggesting the use of tubular drilling methods. These cores, studied by researchers including Jean-Philippe Loa and later engineers, show patterns that imply steady rotational cutting. Yet the depth and consistency of these grooves have sparked debate. Some analyses suggest that the implied feed rates, the speed at which the drill penetrated the stone, would require levels of force and rotational stability that are difficult to achieve manually. In controlled experiments attempting to replicate these grooves using copper drills and sand, researchers have struggled to match the same efficiency without introducing modern mechanical assistance. While these findings do not conclusively prove the use of advanced technology, they do highlight a discrepancy between theoretical capability and observed results. Comparative analysis with other ancient civilizations further emphasizes the anomaly. In Mesopotamia, stone construction was largely limited to softer materials, with baked brick dominating architectural practice. In the Indus Valley, stonework was precise but rarely approached the scale or hardness of Egyptian granite projects. Even the Romans, renowned for their engineering achievements, preferred marble and limestone, reserving granite for columns that were typically shaped with less demanding tolerances. Nowhere else in the ancient world do we find a consistent combination of massive monolithic granite structures and near-perfect internal geometries like those in the Serapeum. This uniqueness raises the possibility that Egyptian craftsmen developed specialized techniques that have not been fully documented or preserved. Another layer of complexity arises from the absence of transitional artifacts. Technological development usually leaves behind a spectrum of evidence: early attempts, imperfect versions, and discarded tools that illustrate the learning process. In the case of the Serapeum boxes, such a progression is not clearly visible. There are no widely accepted examples of unfinished boxes showing intermediate stages of precision, nor are there surviving tools that can definitively account for the level of workmanship achieved. This absence has led some researchers to propose that key elements of the technology, perhaps organic components like wooden frameworks, ropes, or even specific abrasive mixtures, have simply not survived the passage of time. Others argue that the archaeological record may be incomplete due to limited excavation in certain areas of Saqqara, leaving open the possibility that future discoveries could fill these gaps. The logistical context of the Serapeum further complicates the tool question. The boxes are housed in underground chambers connected by corridors that, in some sections, offer only minimal clearance around the containers themselves. If the boxes were carved entirely at the quarry and transported intact, this would require moving 70-ton objects over a distance of more than 800 kilometers from Aswan to Saqqara, then lowering and positioning them with extreme precision in confined spaces. Alternatively, if finishing work was performed inside the tunnels, craftsmen would have had to operate in low-light restricted environments, maintaining consistent alignment over large surfaces, again raising questions about the tools and methods used. Neither scenario is fully supported by direct evidence, leaving both as plausible but incomplete explanations. Archaeological campaigns throughout the 19th and 20th centuries have provided valuable context but have not resolved these technical uncertainties. Mariette's initial excavation revealed inscriptions linking the site to the burial of Apis bulls, and subsequent studies have confirmed the religious significance of the complex. Radiocarbon dating of organic materials and stylistic analysis of inscriptions place the primary use of the Serapeum in the late period, though some elements may date back earlier. Yet despite this chronological framework, the technological aspect remains elusive. The boxes themselves, largely devoid of elaborate decoration, offer little in the way of explanatory inscriptions regarding their manufacture, focusing instead on their ritual function. In summary, the Serapeum boxes at Saqqara represent a convergence between what history understands and what still remains unexplained. Although the ancient Egyptians were undoubtedly skilled engineers, the gap between the tools we know of and the precision achieved remains a major question. This gap may be due to lost techniques, an underestimation of ancient craftsmanship, or simply the limits of current archaeological evidence. But to this day, no definitive explanation exists. In your opinion, what tools did the ancient Egyptians actually use to achieve such near-perfect precision? Lost techniques, or something we still don't understand? Share your thoughts in the comments below. The story of the extraordinary polishing inside the Barabar Caves begins not with what we see, but with what we cannot explain. Carved into some of the hardest granite formations on Earth, during the reign of Ashoka the Great in the 3rd century BCE, these chambers represent the oldest surviving rock-cut caves in India, yet they also present one of the most technically perplexing surfaces ever produced in the ancient world. Upon entering caves such as Sudama or Lomas Rishi, the first sensation is disorientation. Light behaves strangely, reflections shimmer faintly across curved walls, and the stone itself appears less like carved rock and more like a poured polished shell. The granite walls are finished to such a high degree that they achieve what modern engineers would classify as a near mirror polish, with surface roughness estimated in some sections to be below a few micrometers, an astonishing claim considering the technological context of the Maurya Empire. This is not simply smooth stone, it is an engineered surface that challenges the limits of what we believe ancient tools could accomplish. The central mystery lies in the polishing technique itself, a problem that remains unsolved despite decades of archaeological and material analysis. Granite, with a Mohs hardness of approximately 6 to 7, is notoriously difficult to shape, let alone polish to a reflective finish. In modern industry, achieving such a surface requires rotary machinery, its progressively finer abrasives, often diamond-based, controlled pressure and consistent motion across the entire surface. Yet in Barabar, this finish extends seamlessly across walls, ceilings and curved junctions, even in areas that would be physically difficult to access with large tools. Archaeological evidence suggests that Mauryan craftsmen had access primarily to iron implements, possibly hardened through early metallurgical techniques, but there is no direct evidence of advanced abrasive compounds, rotary devices or polishing rigs that could account for such uniformity. Excavations conducted during the 19th century by Alexander Cunningham, followed by further surveys in the 20th century, documented the polish extensively, but failed to uncover any workshop remains, toolkits, or debris fields that would indicate how the process was executed. Several hypotheses have been proposed, yet each collapses under closer scrutiny. One widely cited theory suggests that the surfaces were gradually smoothed using a combination of sand, water, and manual abrasion, a method known from other ancient contexts. However, experimental archaeology has demonstrated that while such techniques can produce a reasonably smooth finish, they fall dramatically short of the reflective quality observed in Barabar. Even after prolonged polishing, microscratches remain visible under magnification, and the surface lacks the optical continuity seen in these caves. Another hypothesis proposes the use of plant-based or mineral polishing pastes, possibly containing fine-grained silica or other abrasive particles. Yet no residue of such substances has been identified on the cave walls, nor have any production sites for these materials been found in the surrounding region. A more speculative line of thought suggests the existence of a lost or highly localized technique, one that emerged during the Mauryan period and disappeared soon after. This idea gained some support from the fact that no later Indian rock-cut sites, including the far more elaborate caves at Ajanta or Ellora, replicate the same level of polish. If the technique were known and practical, its disappearance from subsequent architectural traditions is difficult to explain. Comparative analysis further deepens the mystery. In ancient Egypt, for example, granite was also quarried and shaped with remarkable precision, particularly in structures like the sarcophagi of the Serapeum of Saqqara. Yet even there, the internal surfaces, while finely worked, do not exhibit the same continuous mirror-like finish across large areas. Tool marks, subtle irregularities, and variations in reflectivity are still detectable. In contrast, the Barabar Caves present a consistency that suggests either a highly controlled process or a fundamentally different approach to surface finishing. Similarly, in Mesopotamian or Anatolian contexts, polished stone is typically limited to smaller objects or decorative elements, not entire architectural interiors carved from solid granite. The scale at which the Barabar polish is applied, entire chambers with curved geometries, sets it apart from nearly all known ancient stoneworking traditions. Quantitative observations add another layer of intrigue. Measurements taken in selected chambers indicate that deviations from geometric symmetry are minimal, with curved ceilings maintaining consistent radii and wall alignments remaining true over several meters. Such precision would require not only advanced polishing, but also careful pre-planning of the excavation process itself, ensuring that the final surface could be uniformly treated. The absence of transitional zones, areas where polishing begins or ends, suggests that the entire chamber was finished as a continuous operation rather than in segmented stages. This raises practical questions. How was lighting managed during the process? How were workers able to maintain consistent pressure and motion across surfaces that curve inward? And how was quality control enforced without modern measuring instruments? Archaeological campaigns have repeatedly returned to these questions without definitive answers. Surveys in the mid-20th century focused on microscopic analysis of the stone surface, attempting to identify tool signatures or abrasive patterns, but results were inconclusive. Later studies considered the possibility of chemical treatments, perhaps mild acids or plant extracts used to etch and smooth the surface. but again no chemical residues or reaction layers have been conclusively identified. The caves themselves offer no inscriptions detailing construction methods beyond dedicatory edicts attributed to Ashoka, which emphasize the religious function of the spaces rather than their technical creation. This silence in the historical record is striking, especially given the apparent sophistication of the work. The acoustic properties of the caves provide an indirect clue, though they deepen rather than resolve the mystery. The highly polished surfaces reflect sound waves with minimal absorption, producing strong echoes and resonance effects. Some researchers have suggested that this acoustic behavior may have been intentional, possibly enhancing ritual chanting or meditative practices associated with the Ajivika sect, to whom the caves were dedicated. If so, the polishing was not merely aesthetic but functional, implying a deliberate understanding of how surface finish influences sound propagation. Yet even this interpretation does not explain how the finish itself was achieved, only why such effort might have been invested. Perhaps the most puzzling aspect is the apparent discontinuity in technological development. The Mauryan period is known for significant advancements in administration, art, and architecture, yet the specific technique demonstrated in Barabar does not appear to evolve into a broader tradition. Instead, it emerges abruptly, reaches an extraordinary level of refinement, and then vanishes from the archaeological record. This pattern contradicts the typical trajectory of technological innovation, where methods are gradually improved, adapted, and transmitted across generations. In the case of Barabar, we see the opposite, a peak without a visible foundation and a disappearance without a trace. For modern researchers, the polishing technique at the Barabar Caves remains an unsolved mystery that cannot yet be replicated. Despite measurements, comparisons, and numerous experimental attempts, the true process still lies beyond our understanding. It may represent a lost technology, or perhaps we are underestimating the capabilities of ancient civilizations. Either way, Barabar forces us to rethink how technological progress works, not always linear, and sometimes extraordinary achievements can appear and vanish without ever leaving behind an explanation. What do you think? Was this a lost technology, or are we completely underestimating the capabilities of ancient civilizations? Share your thoughts in the comments below. Suspended in silence, made only of twisted fibers and carefully tied knots, the Kipu of the Inca civilization does not look like a writing system. Yet it may represent one of the most sophisticated forms of information, encoding ever created without ink, parchment, or symbols. At first glance, it appears deceptively simple, a main chord from which dozens, sometimes hundreds, of smaller strings hang, each punctuated by knots. But the deeper researchers have examined surviving quipus, more than 800 documented specimens discovered across Peru, Bolivia, and Chile, the clearer it becomes that this system may have operated far beyond basic accounting. It may, in fact, represent a lost form of language, one encoded not in words but in structure, color, and spatial logic. The earliest detailed Western accounts of quipus date back to the 16th century, recorded by Spanish chroniclers such as Felipe Guaman Poma de Ayala, who described officials known as quipucamayok, trained specialists capable of reading these knotted chords with remarkable speed and accuracy. According to these accounts, quipus were used to track census data, taxation, agricultural output, and even historical records across an empire that stretched over 4,000 kilometers along the Andes. Archaeological discoveries at sites like Puruchuco in the 1950s revealed entire administrative centers where quipus were stored alongside storage facilities filled with maize and textiles, suggesting a tightly integrated system of data management. One cache alone contained more than 30 quipus, and each differing in color schemes, knot density, and structural arrangement, far too complex to be dismissed as simple tally devices. From a purely numerical perspective, quipus are astonishingly precise. Researchers such as Gary Urton have demonstrated that many quipus encode numbers using a base 10 positional system, where the placement and type of knots correspond to units, tens, hundreds, and beyond, remarkably similar to modern decimal notation. In some cases, decoded quipus have been cross-referenced with Spanish colonial records, revealing near-perfect matches in population counts and tribute data. But this is where the clarity ends and the mystery deepens. A significant portion of surviving quipus, possibly more than half, do not conform to any recognizable numerical pattern. Their knots vary irregularly, and their colors shift without obvious correlation to quantity, and their branching structures become increasingly complex, resembling not ledgers, but something closer to syntax. It is within this ambiguity that one of the most provocative hypotheses emerges. The quipus may encode language itself, not through written symbols, but through a multi-dimensional system of variables. Unlike alphabetic or logographic scripts, which rely on visual representation, quipus operate through a combination of features: fiber type, cotton versus alpaca, color, with over 20 distinct shades identified, twist direction, S-twist versus Z-twist, knot type, single, long, figure eight, knot position, and hierarchical branching. When these variables are combined, the number of possible permutations expands exponentially. Some estimates suggest that a fully realized quipu system could encode thousands, if not millions, of distinct informational states, comparable in scale to early computational encoding systems. This has led scholars to draw parallels between quipus and binary or even digital data structures. In modern computing, information is encoded through combinations of bits, zeros and ones, arranged in sequences that gain meaning through structure and context. In quipus, the equivalent may lie in the interplay between physical properties. A red alpaca cord with Z-twist and a figure-eight knot at a specific position might represent a completely different concept than a blue cotton cord with S-twist and a long knot, even if both contain the same number of knots. In this sense, a quipus may function less like spreadsheets and more like databases, layered, relational, and context-dependent. A breakthrough moment came in the early 21st century when researchers working with the Harvard Kipu database project began digitizing and cataloging quipus in unprecedented detail. By analyzing patterns across hundreds of samples, they identified recurring structural motifs, clusters of chords that appeared to follow consistent arrangements, suggesting standardized encoding conventions. In one notable case, a group of quipus from the Santa Valley showed striking similarities in both color sequencing and knot placement, leading researchers to propose that they may have recorded narrative information, possibly even names, events, or administrative instructions, yet without a bilingual reference, a Rosetta Stone equivalent. These interpretations remain speculative. Further complicating the picture is the regional variation observed in quipus. Specimens recovered from coastal areas differ significantly from those found in highland regions, not only in material composition but in structural design. Some quipus feature tightly organized symmetrical layouts, while others appear almost chaotic, with irregular branching and inconsistent knotting. This diversity suggests that quipu usage was not monolithic, but adapted to local administrative or cultural needs, raising the possibility that multiple dialects of quipu encoding may have existed simultaneously. If true, this would make decipherment even more challenging, as there may be no single key to unlock the entire system. Indeed, the destruction of quipus during the Spanish conquest adds another layer of irretrievable loss. Colonial authorities, viewing quipus as tools of pagan administration or potential instruments of rebellion, systematically confiscated and destroyed thousands of them. What survives today is likely only a fraction, perhaps less than 10% of the original corpus. This means that entire categories of encoded knowledge may have vanished before they could ever be studied, including possibly the very examples that would have provided the missing link between Kipu and spoken language. And yet, despite these limitations, the evidence continues to point toward a system of remarkable sophistication, but experimental reconstructions have shown that trained individuals can learn to read numerical quipus with high accuracy after relatively short periods of study, suggesting that the original Quipika Mayok operated with a level of fluency comparable to modern data analysts. More intriguingly, some Andean communities have preserved oral traditions describing quipus as devices capable of recording stories, laws, and even songs, claims that, while difficult to verify, align with the structural complexity observed in archaeological specimens. When placed in a broader historical context, quipus challenge fundamental assumptions about the nature of writing and information. Civilizations such as those of Mesopotamia and Egypt developed scripts based on visual symbols, cuneiform and hieroglyphs that evolved into written languages. The Inca, by contrast, appear to have developed a system that bypassed visual representation entirely, encoding meaning through tactile and spatial relationships. It is a radically different approach, one that may reflect a distinct cognitive framework for processing and storing information. In this light, the Kipu becomes more than an artifact. It becomes a conceptual anomaly. It suggests that complex communication systems can exist outside the boundaries of what we traditionally define as writing. And more unsettlingly, it raises the possibility that we may be looking at a fully developed language, one that we simply lack the tools to recognize. Because if meaning in a Kipu is not carried by symbols, but by the relationships between physical variables, then deciphering it may require not just translation, but a fundamental shift in how we interpret data itself. Is the Kipu just an ancient accounting tool? Or could it be a lost language we still don't understand? Share your thoughts in the comments below.